Okay, so I think we can start this session. So it's a pleasure for me, Jean-Yves, and Mariela to welcome you to the second day of the Emergent Transport Phenomena in Functional Quantum Materials Symposium. So today we will see different ways of manipulating and inducing novel properties in quantum materials. So not only superconductors, as we saw yesterday, but also other kind of correlated materials. So this is more or less the program of the morning. We will have two sessions, one in general on quantum materials, and the second one more focused on the metal to insulator transition. And the first invited speaker is Michele Fabrizio from SIS in Trieste, and he's going to talk about the transient cooling of excitation in carbon-based superconductors. So before starting, a couple of indications. Obviously I will give an alert to the speakers a couple of minutes before the end of the time. And if you want to make questions, you can either write on the chat, or after the talk we will give some space to questions. So after the talk you can switch on your camera and make the question. So we also invite you to clap your hands when the talk is finished, and that's more or less all. We kindly also ask you to use your name and surname as the name written in the Zoom window in order to recognize you when you have to make a question. So I think that's all. So I leave the stage to Michele. Now I stop sharing.
Can you see the window?
Yes.
Okay. So first of all, I would like to thank the organizer of this session. And since this is my first talk on remote, I hope it is not too boring. So today, this is the outline of the talk. I will first give you an idea of a simple mechanism to cool down low frequency excitation by impulse perturbations. Next, I will present results on an exactly resolvable toy model that realizes this cooling. And finally, I will discuss a possible physical realization in alkali-doped fullerenes. Now, let me first discuss this mechanism. I take a metal at finite temperature. And so the metal will have a thermal population of particle Hall excitations, which go down up to 0 frequency. And on top of that, I will assume there is a localized mode, which is poorly populated at these temperatures. However, this mode is coupled to the light, so that within what is called the rotating wave approximation, when the laser is on, the energy to create this excitation is the original energy minus the frequency of the laser. Therefore, when the laser is on, effectively, this high energy excitation is pushed down in energy. And if happens to overlap with the particle Hall continuum, there will be a puring out of low energy excitations from the particle Hall continuum into this high energy mode. So it follows that when the laser is switched off, we will end up with a population of particle Hall excitation, which is decreased as if the system were cooler than it was initially. And the missing energy is stored in the energy mode, And evidently, the system remains trapped in this situation until the high energy mode decay back in the continuum. Now, this is just a picture. The question is whether there is any physical meaning of that picture, which I will try to convince you is the case, discussing the results of an exactly solvable toy model. The model is rather simple. It's just two fully connected quantumizing models with transverse field H1 and H2, which are coupled together. Now, this model becomes exactly solvable in the limit, in the thermodynamic limit, namely in the limit in which the spins for each species n goes to infinity, for the simple reason that mean field becomes exact in the limit n going to infinity. Now let me discuss first what is the phase diagram of a single copy of these quantumizing models. Now, as a function of temperature and as a function of the transverse field. Now, at zero temperature, the model has a quantum critical point that separates a phase where symmetry is broken from at low transverse field, from a phase at high transverse field when the symmetry is unbroken. If the transverse field is below this critical point, then increasing the temperature, you will find a transition, second order phase transition, from the symmetry broken phase to a state in which the symmetry is restored. Now, I will assume that the first Ising copy has a transverse field which is below this critical one. So this is H1. While the second Ising copy has a transverse field which is bigger than the critical one. So that if the two Ising copies were decoupled, only the first one would undergo a transition from ordered to disordered phase, while the second copy would be always disordered. Now, if I couple the two models with a very weak perturbation, then when the symmetry is broken in the Ising copy 1, this will bring also the Ising copy 2 to a symmetry broken phase, although the order parameter will be very, very small. Therefore, the phase diagrams looks practically the same as for the first Ising copy without the second one, namely increasing the temperature, the system passes through a second order phase transition. However, because there are two energy scales, H1 and H2, there are two different excitation energies, one higher than the other. And therefore, for a temperature, say, for instance, just above the critical temperature, there will be a sensible occupation of the low energy excitation, while a vanishingly small occupation of the high energy excitation. So what I will do, I will, making connection with the previous picture, I will assume that the energy excitation plays the role of the energy mode, while the low energy excitation plays the role of the particle continuum, although it's not a continuum. Now, what is the laser pulse in this toy model? This is a perturbation that modulates the coupling between the two Ising copies. In this expression, E0 plays the role of the electric field amplitude. Tau is the pulse duration. And finally, omega is the laser frequency, and I will assume to be at resonance, namely that the frequency is just equal to the energy difference between the high and low energy excitation. Now let me show you results on the dynamics can be also solved exactly. So let me show you results above the critical temperature and switching on the laser in the presence of the laser pulse. So as you see from here, when you switch on the laser during the laser pulse, which is up to t equal tau, the population of the energy excitation increases at the expenses of the population of the low energy excitation that decreases. And consequently, the energy, the internal energy of the isentropic 2 increases, compensating the decrease in internal energy of the isentropic 1. However, the decrease of the internal energy of the isentropic 1, which is the responsible of the symmetry breaking, make a very strange situation. Namely, you start above TC, therefore at the beginning the order parameter is 0. Then you switch on the laser, at some point the order parameter becomes finite and oscillate around a finite value for very long times. Now, this is very simple mean field model, so there is no dissipation. However, if one look at the time average of the order parameter, one sees that the order parameter becomes finite despite the temperature is bigger than the critical temperature, and very gradually go to the equilibrium value, which would be vanishing order parameter. However, this is a very simple model. There is no dissipation, so one can do something better, namely add some dissipation via the Lindblad equation. Now, locally, the system comprises 4 states: the ground state without excitation, the first excited state with one lowest energy excitation, then the next steady state with the high energy excitation, and finally the highest energy state where both excitations are present. Now, in the Lindblad formalism, one introduces what are called jump operators that describe the decay of a high energy state into low energy one, and the opposite process. And these two processes are related by detailed balance, where beta is the inverse temperature of the dissipative bus. Now, if all jump operators are of the same order of magnitude, we find that the system relaxes very fast to thermal equilibrium, there is no cooling. While if the jump operator grow with the excitation energy, namely if the high energy excitation decay faster than the low energy one, which is a reasonable assumption, then we do find cooling. Now, I will show result assuming that the high energy excitations decay 600 times faster than the low energy excitation. In addition, I will assume that the temperature of the bus is 1.5 bigger than the critical temperature, and I will vary the electric field amplitude and the pulse duration in such a way as to keep the fluence constant. Now, this is, for instance, one result. So this is the order parameter that I showed you as before. This is the profile of the pulse. And this is the integration of the Lindblad equation for the order parameter. As before, what you see is that the pulse creates a finite order parameter, despite the temperature is bigger than the critical temperature, which finally goes to 0. And in this case, there is actually relaxation to the thermal equilibrium. However, if I now increase the pulse duration and decrease the peak amplitude, so to leave the fluence constant, we find a very strange result, namely that the order parameter remains finite the longer the bigger tau is a constant fluent. You see, this is the lowest tau, then you increase tau, and you, until, for instance, at this value, you find a situation in which the order parameter remains finite for rather long time. Now, so far, this is just a toy model. And now let me discuss a possible physical realization of this cooling. Now, this is by now a 4-year-old experiment by the Cavalieri group. At the end of the talk, I will show you more recent results. This is a pan probe experiment of alkali-doped fullerenes, which are molecular superconductors. The pan pulse has a duration of 300 seconds, the frequency in the mid-infrared range, and the probe is simply optical response. Now, these are the results of the pan probe experiment. In red is the real part of the optical conductivity at different temperature below and above the critical temperature. So below, you see the opening of the superconducting gap, which disappears above, where you find 20 milliV through the peak. Now, if you do the same, if you measure the optical conductivity 1 picosecond after the pulse, what you observe is that somehow the gap opens again. So there have been many post-explanation of this remarkable result. So I will just present our, comparing what happens in this out of equilibrium situation with what happens at equilibrium. At equilibrium, as you go across the superconductor to normal metal transition increasing temperature, unlike what you expect in a BCS superconductor, the gap does not close, but is filled by thermal excitation. So this is very common to many correlated superconductor. But if you compare this situation with the out of equilibrium experiment, then you may argue that the laser pump, what it does simply is to clean out thermal excitation within the gap, as if you effectively cool the system at low frequency. Now, the other important observation is that this superconducting-like response is observed only when the laser pulse hits a mid-infrared peak that is observed at equilibrium. Okay, so this is a mid-infrared peak which is centered around 50 millieV, and only in this case you do find this transient superconducting-like behavior. So from this point of view, this experimental data looks reminiscent of our cooling mechanism, namely you pump into an energy excitation and you cool down low energy ones. Now, the key issue is to understand what is the high energy excitation that is responsible of this mid-infrared peak. And okay, what we did some molecular calculation, and this molecular calculation suggests that this peak derives from a spin triplet molecular exciton that corresponds to the LUMO to LUMO plus 1 molecular transition, which is strongly pushed down in energy by the positive interplay of the Coulomb exchange and the strong Jahn-Teller effect known to be active in fullerene. Now, what is the absorption process in diagram? Okay, the photon creates brings an electron from the LUMO to the LUMO plus 1, but then via the magnetic exchange present in the system, this excitation becomes the spin triplet exciton and the spin triplet particle hole excitation in order for the spin to be conserved. In formulas, the absorption is the convolution between the exciton density of states and the imaginary part of the dynamical magnetic susceptibility, which is large in K3C60, which is not far from being an antiferromagnetic Mott insulator. Now, if we take an exciton density of states, which is a very narrow Lorentzian centered around 20 to 30 millieV, and we take for the dynamical susceptibility Fermi liquid expression with parameter known realistic for fullerene, we find a line shape like this, fixing the only unknown parameter, which is this prefactor, which is the dipole strength of this transition. in such a way that the maximum corresponds to the maximum observed experimentally. I want just to emphasize that the width of the peak is not controlled by the width of the exciton density of states, but rather by the width of the imaginary part of the dynamical magnetic susceptibility, which can be much bigger than the width of the exciton. Now, let us move to the experiment and assume Fermi liquid theory is valid, as well as local equilibrium. Now, in this case, one can write very easily down dynamical equation, namely the rate of change of the quasi-particle energy, which, because of local equilibrium, is equal to the specific heat times time derivative of the effective temperature, should be equal to the energy per unit of time absorbed by the laser minus the energy still per unit of time that is stored in the exciton. And the absorption is simply the same expression as before, with the temperature, which is the instantaneous local equilibrium temperature. Now there are two assumptions in this expression. One is the assumption that the exciton density of state is now a delta function centered in the exciton energy. And the other assumption is that the local equilibrium is controlled only by the temperature, assuming that for the chemical potential remains constant, which might not be the case. However, under this assumption, we can write very easily down a first order differential equation for the instantaneous temperature, which is nonlinear equation, since both the specific heat and the absorption depends on the same temperature. And because of our assumption, what is clear from here, that the temperature goes down if the frequency of the laser is below resonance, so is smaller than the exciton energy, and the temperature goes up in the opposite case. This is a trivial result, because if the frequency of the laser is not enough to excite the exciton, you have to absorb particle Hall excitation in order to excite the exciton, which implies that you effectively cool down the particle Hall excitation. Now, if we integrate this equation up to the duration of the pulse, starting from some initial temperature, we find that the temperature at the end of the pulse can be quite lower than it was initially, and even lower than the critical temperature. Therefore, the system in this simple modeling has effectively cooled down. Now, let me end mentioning a recent result still by the Cavalieri group. Now, they repeated the same experiment, now using a different laser, a CO2 laser, which has a lower frequency than the original laser. But now what they can do is that they can increase the laser pulse duration, leaving the fluence constant, because otherwise, with a very long pulse, one would destroy the sample. And what you find, this is the loss in spectral weight. What you find is that the transient superconducting state lasts longer and longer, the longer is the pulse. Not, I mean, at least up to 550 picosecond. And it lasts, this is the time dependence of the spectral weight loss. And you find that this transient superconducting state lasts even of the order of nanoseconds. Now, with these times, they can also do a full contact resistance measurement, and they found indeed that this transient state is accompanied by a drop of the sheet resistance almost to zero. That remains for a very long time. And with that, I concluded. Before putting my conclusion, I will acknowledge all my collaborators, in particular Andrea Nava, who was postdoc in CISA at the time of these works. And these are my conclusions. So I just presented you a very simple and general mechanism to transiently cool down low frequency excitation that might explain the light-induced enhancement of TC that is observed in alkali dope fullerenes. And this mechanism is rather simple. It just requires an high energy excitation that acts as an entropy sink for low energy excitation when the laser is on, and when the laser is off, it very gradually releases back all the entropy so that the system for a long time looks as if it were effectively cooled down. And with that, I thank you.
Thank you. Thank you, Michele, also for, you were perfectly on time. Okay. Okay, so now we can leave space for questions. You can either use the chat or raise your hand, switch on your microphone, as you prefer. In the meantime, I start with a very general question. So, in the case of fullerenes, I mean, they are rather close to the Mott transition. But in general, would you say that, I mean, it's important to achieve this regime in which you have the transient cooling to be close to a Mott transition or to have strong correlations? So would you say that there is a sort of general rule or general indication then being close to the Mott transition would help in this direction?
In the specific case of fullerenes, this is important because you need to have many low energy thermal excitation, particle excitation, and this is the case because these are magnons effectively, because these are spin 1 particle excitation, and you want to cool down these magnons, but namely you should have a lot of magnons in order to decrease substantially the temperature, and this happens because the system is closed to be an antiferromagnet. Now, in general case, or namely considering the simple picture I gave you at the beginning, you don't need some assumptions. So this is a rather general picture with only needs that there are many particle excitation that are thermally populated. And so this high energy mode can pour out a lot of thermal excitation so as to effectively cool down the system. Okay, so
being close to the Mott insulating phase, I mean, it's a peculiarity of the fullerenes, but in general, you don't need to work on a strongly correlated material. No. So okay.
You must have a lot of fluctuation, low energy fluctuation that you want to get out of the system.
Okay, so again, generally speaking, if you had to give a recipe, I mean, for experimentalists, so you need to have a system, okay, with the well-defined mode with a lot of fluctuations, and then a continuous state. So that's enough.
Yeah.
Okay. Thanks a lot. So there is a question from Fernando Sols Lucia. You can switch on your microphone.
Yeah, thank you. Yeah, I have a question. Have you worried about the limits that you may have to the rate of cooling, in the sense that if you might want to cool things very fast, for instance, right? But if you do it too fast, maybe you have problems with the acceptability principle. So there might be a quantum limit to the speed. That's an issue I have discussed somewhere. So I wonder whether you could face those limits or probe these limits in this context.
Now you can probe these limits in this simple model clearly. Now, evidently, what matters in this model is the coupling between the low energy. So the coupling between these two Ising species, it is like a coupling between the low energy and the energy excitation, okay? So this coupling introduces a natural time scale in the system. Now, if your pulse is too short with respect to time scale of this is connected to the excitation, then you will not have enough cooling. So there is clearly you have to fix the time, the laser pulse duration in such a way as to give the system enough time for the low energy excitation to go into the energy ones. Otherwise, it does not work.
Okay, so do you think you could understand in terms of also quantum uncertainty, in the sense that if you do things very fast, the energies are not very well defined, and therefore the temperature is not well defined?
Even, yeah, you can put also in this case, in this way, yeah.
Okay. Yeah.
Okay, so is there any other question? You can raise your hand, type the question in the chat.
I have maybe a short question. In the experiments that you showed on the Furans,
the first one or the last one?
The last one that you showed, actually, that they do measure the decrease of the resistance. You know, because there the time scales is much, well, still more similar. No, I was wondering, I mean, you did say it, I think it's like, so as long as the laser is on, they can keep the superconducting states like that, right? So in principle, it's as
yeah, essentially, I mean, the longer is the pulse. So if you have a very long pulse, you stabilize a quasi steady state, which looks like, which is effective superconducting, which is not very different from what you found, what you find. So in the conventional superconductor, if you pump in the microwave, in this case, the difference is that you pump much above the superconducting gap.
Yeah. Thanks.
Yeah, Michele, coming back to this point, actually, also in a conventional superconductor, if you pump below gap, you change the distribution of the quasi-particles, and you have an effective cooling.
Yeah, it's exactly the same. The only difference here is that you pump much above the gap.
Yeah, and the trick is that you are using this bosonic mode, which is located above the gap. Yeah. Okay. I see that there is Carlo Di Castro. There's a question from Carlo Di Castro. You can switch on your microphone.
Yeah. Michele, hi.
Oh, Carlo.
Listen, I have a question similar to the one you had previously. What happens if you if you have a situation like that you described? Could you switch on the quantum critical point of a system who is not becoming critical in a finite temperature in such a way that the behavior will show up as a quantum behavior at a higher temperature than to 0 only? I have in mind a situation where you have let's say charge fluctuations at T equal to 0, but not is critical at t equal to 0, but not at t different from 0 because it's a low dimensionality system. And however, you have a lot of fluctuation about this phase which show up at t equal to 0. Could you have, in this situation of, let's say, dissipative coupling, have it transfer what happened at t equal to 0 to t different from 0?
In principle, if I understand correctly what you ask, okay, yes, in principle, if the, so let me go back to this model. So,
yeah,
this would be your quantum critical point.
Yes, and there is no criticality.
In this case, you don't have order and disorder because.
Yeah, so the disorder happening only at t equal to 0. Could you, by this pumping or this dissipative coupling, have a situation where you show it above t equal to 0? Could you push upwards?
Upwards to, you want to say to heat the system rather than cool?
Exactly.
I think
could you pump in, let's say?
Yeah, I think that usually you heat the system when you pump, okay? So only in this particular example, in which we have very different energy excitation.
Yeah, but the transient would be similar, or?
No, the transient would be different, completely different.
But it will have a normal slowing down, or it will have a peculiar slowing down?
No, that I don't know.
Okay.
It's a good question, but I don't know.
Okay. Thank you, Michele. Bye.
Thank you. Ciao.
Okay, any other question? Michele, I have just a last curiosity. So in this case, basically you showed that you can cool down and go across a second order phase transition, for example, superconductivity. But in principle, is it possible also to go through also first order phase transition? So for example, an insulator to metal transition, so from the metallic phase to the insulating one? Huh?
Yeah, sure.
Even if you have a latent heat, so it's just an issue of how much you pump the system.
Yeah. You would find exactly the same. Clearly, it will be a little bit more difficult in that case because you need to overcome a barrier to stabilize the order phase. But in principle, yes, it should work exactly the same.
Okay. So many thanks, Michele.
Thanks to you. Bye.
I think we can move to the next speaker, who is Ruben Gracia. Hey. Ruben, okay. So you can share your screen.
Good morning. Okay.
Good morning. Welcome.
Thank you.
And okay, Ruben is going to talk about the. Okay.
Can you see it?
Yeah, we can see it. Okay.
Okay.
Okay, we can see. Okay, so I will give you an alert when you have 3 minutes left. Okay.
Okay, perfect. Thank you.
Okay.
So welcome. My name is Ruben Gracia, and I am a PhD student for the University of Zaragoza in Spain. I'm going to present my work about weak anti-localization effect in bismuth selenite thin films that I've carried out under the supervision of Jose Maria de Teresa and Soraya Sangiao, and in collaboration with Pasquale Orgiani and Chiara Vigi from the CNR in Italy. So this is the outline of the talk. First, I will say, first I'm gonna change to the laser pointer, okay. First, I'm gonna say a few words about topological insulators. I will introduce you the weak anti-localization effect, and I will say some properties about bismuth selenite. I will follow with the experimental methods, then I will show you some main results and some discussion. and I will close with some conclusions. So first, let's start by the definition of topological insulators, that are materials that behave as insulators in their interior while supporting metallic surface states at their boundaries. So the first question is, what do we need to obtain a topological insulator? We need basically three ingredients. We need first a band inversion that can be produced by a strong spin-orbit coupling in the interior of the material that leads to a change in the topology of the bulk band structure. We need also an interface with a trivial insulator that can be, for example, vacuum. And at that interface, the topology changes, and that gives rise to boundary states. Well, that in three dimensions, we have surface states, and those surface states must be protected by some symmetry. And in this case, the symmetry is time reversal symmetry. So from these three ingredients, what we obtain is some surface states with a pi-Barish phase and a spin momentum locking that are protected against non-magnetic impurities. Those surface states are accommodated in a Dirac-like dispersion relation called Dirac cone, like you can see here. And the red arrows here represent the spin orientation that is coupled to the direction of the momentum perpendicularly. So in this kind of materials, we can observe many interesting phenomena, and one of them is the weak anti-localization effect that takes place at low temperatures when the carriers enter the quantum diffusive regime and the phase coherence length becomes much larger than the elastic mean free path. So in that situation, the carriers can move through the material, being scattered from one impurity to the other, while keeping their quantum phase for long distances. So in some cases, they can perform closed paths, like this one, in which the distance is shorter than the coherence path, than the coherence length, sorry. So interferences can take place. In this case, for example, they can go through the blue path, or quantum mechanically, they have the same probability of going through the time reversal version, which is the red one. And from a quantum mechanical point of view, they can interfere. And as the phase accumulation along each of them is the same, they can interfere constructively. However, when we have a strong spin-orbit interaction, the spin orientation changes along the path, and that induces an extra phase shift between both paths that leads to a destructive interference. And this is translated in a reduction of the probability for the carriers to going backwards, which is translated as well in a reduction of the overall resistivity. And this is called weak anti-localization effect. So we can observe this effect in magnetoresistance measurements. So if we measure the longitudinal resistivity against the magnetic field, what we observed is that at zero field, we have the quantum correction coming from the wall, and the resistivity is lower. But as we increase the magnetic field, the time reversal symmetry is broken, and we introduce a phase shift between the time reversal paths, between this path and the other one. So that destroys the weak anti-localization effect, and as we increase the magnetic field, that quantum correction disappears, and we recover the parabolic dependence in the classical regime. So to study this phenomenon, we apply the Hikami-Larkin-Nagaoka model that provides a correction for the sheet conductance as a function of the magnetic field that is given by this expression. So we can use this expression to fit our experimental data, and we have two free parameters. One is the coherence length, the phase coherence length, and the other one is the spin orbit parameter alpha, that equals to -12 for each coherent channel contributing to the weak anti-localization. So in general, we can find two situations when alpha equals to -12, and then we have one independent channel that can be either the bulk or the surface, or we can have both surfaces coupled through the bulk. Or we can find alpha equal to -1, and we have two independent channels that can be either the bulk plus one surface or the two decoupled surfaces. In this sense, the weak anti-localization can provide very useful information to understand the role of surfaces in transport. So the system we have studied is Bismuth Selenite, which is a 3D TI, a very well-known 3D topological insulator, and it is arranged in quintuple layers, which are the minimum units that keep the stoichiometric of the material. It is very interesting because it is quite simple. It has just a single Dirac cone at the center of the Brillouin zone. As you can see here in this spectroscopy picture, this is the surface cone at the center of the Brillouin zone. And furthermore, it has a relatively large bulk band gap of 0.3 electron volts. That should make easier to study the surface states. However, this is in theory because actually they are not real insulators due to N-type doping coming from selenium vacancies. And this N-type doping populates the conduction band, and then we have the bulk contributing in parallel to transport in parallel with the surface states. So this is why it is very important to make high quality samples. So to study transport in bismuth selenite, we have counted on bismuth selenite thin films with different thicknesses, synthesized by pulse laser deposition and characterized by angle result of emission spectroscopy by Dr. Pasquale Orgiani's group in Italy. This is an example of ARPES characterization of one of our samples. We can see the surface Dirac cone. And we have taken those films and we have patterned them into a whole bar shape by optical lithography. This is an example. So we could inject current through the longitudinal contacts and measure voltage drop across the transfer contacts. So we use these systems to study magnetotransport properties at a PPMS, applying high magnetic fields up to 9 Tesla and low temperatures down to 2 Kelvin. Now I'm gonna show you some results. First, this is the resistivity versus temperature curve. I show here a representation for 3 of our films with different thicknesses. And we observe that the resistivity increases with increasing temperature, which indicates a metallic behavior that reflects the fact that the bulk bands are populated. As I mentioned before, it is not a real insulator. And at very low temperatures, we find insulating ground states due to electron-electron interaction. You can see it here in the insets, that the resistivity increases with decreasing temperature. Well, this is the Hall resistivity, the magnetic dependence of the Hall resistivity, again for 3 different samples. And we have always observed that we have linear dependence, which indicates in principle that we have one type of carrier. And we have always observed a negative slope that indicates N-type transport that is found always in bismuth selenite. And it means that the electrons are the main carriers. So given this, we could apply the Drude's model for one band, and we could extract the transport parameters, the carrier density, and the mobility. So regarding the carrier density, again, for 3 different samples, you can observe that there is a weak thermal activation of carriers. I don't know if you can see it properly, but the variation of the carrier density with temperature is very weak. And as you can see, we obtained always sheet carrier densities in the order of 10 to the 14, 10 to the 15 centimeters to the -2. And this indicates a high number of bulk carriers, because considering that when the Fermi level is located inside the gap, inside the bulk band gap, the sheet carrier density is usually in the order of 10 to the 12. This is called the topological regime because we are only seeing the surface states, but however, we have 10 to the 14 to 10 to the 15 centimeters to the -2, so we are 2-3 orders of magnitude higher than that, and it means that we have a strong contribution from the bulk. So regarding the mobility, I show here the mobility for 3 samples as a function of the temperature, And we observed that it decreases slightly with temperature, which indicates that there is thermal activation of phonons. When we go to the representation against thickness, we observed that the mobility increases with increasing thickness, and this reflects the fact that there is an improvement in the quality of the films as we go to higher thicknesses. Now, the longitudinal magnetoresistance. First, I show here for 3 different samples at 2 Kelvin, the magnetoresistance. We observed at low magnetic fields the correction coming from the wall with this caps like minimum. And as we go to higher fields, we recover the classical regime. What is interesting here is to see that as we go to thinner films, we obtain a stronger sign of weak antilocalization. And this is due to the fact that as we go to thinner films, you confine the movement of electrons in 2D, and you enhance the probability for the electrons to perform close paths. So you enhance the sign of the weak antilocalization. Here we observe for a sample of 15 nanometers, the curves for different temperatures. And what we see is that as we go to higher temperatures, we see that the weak antilocalization is suppressed. And this is because as we increase the temperature, the phase coherence length decreases, and finally it becomes comparable to the elastic mean free path, and the weak antilocalization, the coherence is lost, basically. Okay.
So you have 3 minutes left.
Okay, thanks. So considering those data, we could apply the Hikami-Larkin-Nagaoka model, and we could fit quite well our data to the model. So we could extract, this is a low magnetic fields where the weak antilocalization takes place, the correction, and we could extract the coherence parameters. So this is the phase coherence length that ranges between 60 and 130 nanometers, more or less, and increases slightly with thickness, which reflects again the improvement in the quality as we go to higher thicknesses. And this is the spin orbit parameter that stays always close to -12. This indicates the presence of just a single coherent channel. And considering what we have seen before, we think that the bulk is dominated transport, and it is gonna be present in the coherence transport as well. So now we arrive to the conclusions. Okay, first we found alpha equals to -12 for our bulk dominated films. And we have checked the literature, and we have observed that this value of alpha has been reported many times, and it is nearly always attributed to a coupling between the surfaces through a metallic bulk. And we think this is also happening in our films. We have observed that we have a surface Dirac cone in the characterization, but we haven't obtained the direct proofs of surface transport in our magnetotransport measurements, apart from the strong sign of the weak antilocalization. Regarding the phase coherence length, when putting our values in the context of the literature, we have observed that even though there is a variability in the properties of the film, the coherence length shows a behavior that can be predicted from the mobility of the carriers in the system. So we have represented from the literature the values of the coherence length against the mobility for many samples, and we have found this tendency that has attracted our attention so much. And finally, just to say that the weak antilocalization effect allows one to extract important transport parameters, even though maybe by itself it can't show conclusive proofs that of surface transport, but together with other extra magnetotransport measurements allows a deeper understanding of the role of surfaces in topological insulators. And well, that's all. Thank you for your attention. And if you have any question, let me know.
Okay, thanks a lot, Ben.
You're welcome.
Okay, so yeah, and now it's open for discussion and questions. There's already one in the chat from Gunta Kunakova. If you want to switch on your microphone and make the question directly, it's okay.
Hello, can you hear me?
Hello?
Yeah,
Yes.
I can.
Yeah, so how are the films grown?
Uh,
That's the question.
They were grown by PLD, by pulse laser deposition.
And which substrate did you use?
We used, I didn't mention, sorry. It was sapphire.
Okay, thanks a lot.
You're welcome.
Thanks.
Okay. Okay, so I see some questions in the chat. So Sofia Ferreira Texera, you can switch on your microphone.
Hi, can you hear me?
Yeah,
Yes.
I can.
Thank you for the nice talk, really interesting. I have a question. Have you, you showed different resistivity curves as a function of temperature, but do you know how they change with thickness? Do they increase? Yes.
Yeah, in this case, we see that as we go to thinner thicknesses, to smaller thicknesses, we observe that the resistivity increases, which is, we think it's due to surface scattering, probably, because you are confining the movement of the carriers. But I mean, there wasn't a clear variation when you see all of them together, because we measured like, I don't know, 7 or 8 thicknesses. Sometimes, I mean, you could see that in general, you could see that the resistivity of the film increases with decreasing thickness. That's the general behavior.
Okay, okay. Thank you. I asked because there has been some reports with some oscillations in the transport properties with thickness. So it's also maybe that could be happening with you, but I'm not sure if those oscillations are real or not. So that was my question.
Okay, thanks.
Second question I have is, have you measured, like, for example, Seebeck coefficient as a function of temperature? Because that could also give some insights into the bulk transport versus...
What? Again, please?
The Seebeck coefficient.
No, we haven't measured any Seebeck coefficient yet.
Okay.
But you tell that can provide useful information?
Yeah, it's because with the Seebeck coefficient, you also, like the Hall resistivity, you can also see if it's P-type or N-type. But the Seebeck coefficient depends on the variation of the density of states near the Fermi energy. So that could also give some insights with temperature. Already, if you measure at room temperature, it's already good to know. But with temperature is also an interesting technique to give insights into if it's bulk, if it's surface, what's happening there.
Okay, thank you for the information.
And my last question is just out of interest. If you think at higher magnetic fields, you could see the Shubnikov-the-Haas oscillations or something like that?
Well, that's a good question. I don't know, because I think our mobilities are not high enough.
Mm-hmm.
And I don't know, maybe we could try, but we don't have any certainty right now. So that would be really nice, but we haven't measured any oscillations yet.
Okay. Okay, good. Thank you. Really nice work. Thank you.
Thank you.
Okay, thanks. So we can quickly move to Inge Grön. There's a couple of questions. So I ask you to be rather quick because otherwise we run out of time, but go ahead.
Can you hear me?
Yes.
Okay. I was just wondering if you also trying to use a gate to access the topological state.
Sorry, that was a question for me.
Yeah.
Okay. I stopped sharing my screen.
No,
okay.
it's fine.
Yeah, go ahead.
Okay, I do it again. Sorry, can you repeat the question?
Are you trying to use a gate to access the topological states?
No, not yet.
Okay.
Not yet.
Because
we know it can. We know it can be useful.
Of the weak anti-localization.
We know it can be useful, but we haven't implemented that technique yet.
Okay, and one more quick question. How do you contact the BS for the electronic measurements?
You mean how do we
You
contact,
directly do wire bonding through BS, or?
We have a micro contact machine, so we put contacts. I think it's aluminum contacts from these leads to the platform. I mean, we have like a.
But you don't use like titanium gold contacts or something. It's directly.
Yeah. We evaporate some gold. Some gold here. You can see the image of the.
Yeah, I see it.
Of the sample. Okay, yes. This gray part is the bismuth selenite. Black part is sapphire, the substrate, and this golden part are the gold contacts that we
on top of
evaporate.
The BS.
Yeah, it is an optical lithography step, so it is a lift-off process. So we open some windows at the onto the contacts. So we can evaporate.
How the lithography is done, but I'm just wondering because we are using also BS, but we have problems with contacts. That's why I'm asking.
We use a layer of chromium.
Sorry, guys, to interrupt you.
We can talk later.
We're running out of time, but you can discuss these technical details.
Yes.
Okay.
Thank you.
Perfect.
Thank you. I'm sorry, but otherwise we do not respect the schedule. I mean, there is a very last question from Yarango. This is probably the nickname. Okay. Yeah.
No, it's Isabel, but yeah, okay. Now, have you tried to measure in amorphous bismuth selenite this weak anti-localization?
No, we haven't. In amorphous bismuth selenite, no. No, I think it is always crystalline bismuth selenite. I haven't seen any report about amorphous bismuth selenite, actually. Have you?
No, I am wondering if it's
okay. I don't know, actually. Yeah, I think that maybe the disorder would be too high, I think, in the amorphous system. I don't know, actually.
Okay, thank you.
You're welcome.
Okay, thanks a lot. We can thank the speaker again. Okay, I'm sorry to interrupt the questions, but we have time later. You can directly contact the speaker to discuss the technical details. Thanks a lot. So we move to the next speaker, who is Falco Pienka. Okay, who's going to talk about the transport of optical excitation. So, okay, I think it's working. I leave you the stage. I give you an alert when you have 3 minutes left.
Okay, thanks. I trust you can hear me well. So thanks for giving me the chance to talk here at this nice conference. This talk is a theoretical talk about exciton polaritons in semiconductors. So somewhat different topic now. It has been done together with people at ETH and Atachimogo's group with Richard Schmidt in Munich, Eugene Dammler, and Gary Sarand. But before discussing excitons, let me back off and discuss a rather general concept, which is a quantum impurity in a bath. And some part of this talk will be at this really rather general level. So if you imagine a quantum impurity inside a bath and their interactions, then the bath atoms will be shifted away slightly from their equilibrium position just in the vicinity of the impurity because of the interaction. So there will be a local cloud of polarization of the bath atoms here, and the impurity will form a new quasi-particle, which is generally called the Polaron, which I'll depict by this kind of cloud. And now because the impurity it has some correlations in the path attached to it, this cloud of polarization, it has effectively the higher mass. So polarons always have this mass enhancement, and at the same time, the quasi-particle weight of the impurity is reduced, which meaning the new quasi-particle that's formed has some property that are impurity-like and some properties that are bath-like. And so, famous example of this is, of course, electrons traveling through a lattice, through a crystal. This is the lattice polaron. Because of Coulomb interactions, the electrons shake on the lattice and create a local cloud of phonons in their vicinity. And as they travel through the crystal, they have to drag along this cloud of phonons, making them effectively heavier. Another manifestation of this phenomenon are Fridael oscillations. So this is if you have usually a static impurity inside an electron Fermi C, you get these kind of oscillations nearby, which are oscillations of the density, of the electron density, which are again just a cloud of electronic polarization near the impurity. Now, if you imagine this impurity to be mobile, then it again has to drag along these Fridael oscillations as it moves through the electron Fermi C. So these are two examples: one with a bosonic gas, one with a fermionic gas, and there's some differences, but also many similarities between these two concepts. And so, actually, I want to discuss the case of a fermionic bath in more detail, and assuming that the impurity in our case is an exciton that you can say excite optically if you want. So this is absorption spectroscopy of a two-dimensional semiconductor, molybdenum diselenite. This is energy here, and this is density. And if the density is inside the gap, which is between these two zeros, this is taken from this paper here, then you have a strong exciton resonance at some particular energy in absorption. But then if you dope the system into either conduction band or valence band, then this resonance here blue shifts. I hope you can see that. And then there's a new resonance appearing at somewhat lower energies that also has some dispersion. And so the interpretation of this phenomenon is that the exciton actually forms a polaron. So that you excite an exciton with a hole in the valence band, electron in the conduction band, and then if you have electronic carriers, mobile carriers around, this exciton is interacting with this Fermi C of electrons and is dressed by excitation of this Fermi C. So particle hole excitation around the Fermi level at much lower energies. So one cartoon picture of this would be just an exciton plus a single particle hole pair. You can write down a very simple wave function following GEFES for Fermi polarons, where you have basically a superposition of a bare exciton and an exciton plus a particle hole pair. But crucially, this quasi-particle is still neutral, so it doesn't have any charge because it's really just dressed by a particle hole pair. In contrast to what's called a trion, where you really have a bound state between an exciton and a charge. So this is more like this picture. We'll take out some particular exciton charge out of the Fermi C. So this particle would be charged, whereas this particle is still neutral. And I'm talking about the first one. And the reason for that is that this particle is still much more likely to couple to light. So eventually, I want to talk about exciton polaritons, and light cannot couple very well to trions. This is just an issue of basically matrix elements, that the overlap between a state without a trion and a photon, and the state with a trion is vanishingly low, because you have to basically localize an exciton and an electron at the same place. So what you see in this absorption here is really this kind of polaron, and there are two branches of it. The one is called the higher energy repulsive polaron, and the lower energy attractive polaron that you can see. That's very typical of this polaron formation, which you can see. But now, okay, so this is the context of discussing polarons in the context of excitons and semiconductors. But now I want to discuss transport properties of polarons in a general sense, and then I come back to excitons in just a minute. but first, again, just assume you have a polaron that's inside a bath, so it forms this polarization cloud. And now you pull on all the bath particles with some particular force, F, and that results in an acceleration of the bath particles that I call AB. And now I want to ask the question, will there be a drag force on this impurity? Because now I'm pulling on the cloud of these Polaronic correlations, and as a result, the impurity might also accelerate, even though there's no direct force on the impurity. In order to answer that question, let me go into the co-moving frame where all the bath particles are at rest. But now I've gone into an accelerated frame, so I need to introduce a fictitious force acting on the impurity. And because it's only acting on the impurity and not on the cloud, the mass that I have entered here is the bare mass of the impurity, Mi, times minus the acceleration of the frame, right? So this is typically the fictitious force is minus acceleration times the mass, but what enters here is really the bare mass, because I've really only done a transformation of reference frames that doesn't know anything about Polaronic dressing. But now as the impurity responds to that fictitious force, it will accelerate with its own acceleration AI that is determined by the dressed mass, by m star, because now it accelerates in the co-moving frame. It needs to drag along this cloud of polarization. So the acceleration AI in this co-moving frame of the impurity will be minus the bath acceleration times m over m star, so the bare mass over the dressed Polaron mass. Now, if you go back to the lab frame, you just have to add the acceleration of the frame, and you get an acceleration of the impurity that's equal to the bath acceleration times 1 minus m over m star. So the impurity is actually accelerating in the same direction of the bath. So there is a direct drag force on the impurity. And the prefactor here is between 0 and 1. So it's 0 when there is no interaction. It's really a drag force. When m star is equal to m, then it would be 0, and it's always smaller than 1. And so this is basically the force that I was looking for. You should be careful to distinguish this from what people call what people usually call drag or Coulomb drag in other contexts. Where the drag force is really proportional to a velocity difference of the bath and the particle. And here, this would come on top of that. This is something that I didn't discuss because I didn't discuss scattering events, but this is an additional force that only comes because of the quantum coherent dressing of the impurity by this, because of this Polaron formation that would not be present without this mass renormalization. Okay, so this is kind of a simple argument based, very intuitive cartoon pictures on why this force should be there, and it also doesn't distinguish between fermions and bosons. But of course, we want to do a full quantum calculation to verify that that's the case. And to this end, we did this kind of diagrammatic calculation, so it looks very complicated. But I'll be just flashing this as to underline that there's really a solid calculation behind this. So the description of a Polaron in this case here is in terms of these red lines are exciton Green's functions, and they are addressed by electronic particle hole pairs, these blue lines here, with interactions that are represented by this T matrix, and the T matrix is really just an interaction, a ladder of interaction lines, and this is a good approximation in the limit where the density of excitons is very low. And then to get the drag conductivity, so this drag, you need to evaluate two diagrams that you can get from some conserving approximation. So there are some T matrices here. There are also some vertex corrections with other T matrices inserted in here. So these are rather complicated diagrams. They're kind of similar to Maki-Thompson and Aslamazov-Larkin diagrams in the theory of fluctuations in superconductors. But it turns out you can actually solve them analytically, even including for fermion disorder, and you can actually also include disorder for excitons. And if you expand everything to lowest order in the density of excitons, you find a very simple result, namely it's actually the same result that we found on the previous slide. The drag conductivity is equal to the number density of impurities, so number density of excitons in this case, times the fermionic mobility, times 1 minus m over m star. So this is exactly the same the same result you would get from the simple argument based on reference frames that I gave in the previous slide. And this is ignoring actually excitonic disorder in this case. Okay, so how can we see something like this in experiment? Well, one idea is to, you can just take a semiconductor, in this case here, a picture of a TMD semiconductor, and then shine a laser locally at some point, or put everything in a microcavity and have polaritons, and then apply a current across this and look at the luminescence to come out at some other place. As I said, you can also put the semiconductor inside a microcavity where, basically between two mirrors where the laser is trapped and the excitons form polaritons, hybridizing with the photons. And then the same argument that I just gave should carry through even for exciton polaritons. So this is some way to move around exciton polaritons, effectively photons, with static electric fields, right? As if they were charged particles, even though they are neutral, just because of this polaronic dressing. And you can think even further that, you can also apply a magnetic field and think about a Hall effect of photons and realize, effective gauge fields for photons in this way, because in a magnetic field, the electrons will experience a Lorentz force. And by the same simple argument that I gave previously, any force on the electrons will also be felt by the exciton polaritons through this polaronic dressing. And in this way, you can obtain, an effective gauge fields for the polaritons. And you can even think about putting the electrons in a quantum Hall state and then ask the questions, well, can I generate topological states of polaritons in this way? Okay, but let's to look at the evidence of what is there actually this kind of dressing? Well, this has been shown in this Nature paper in 2017 by Atachi Imamogu's group, where this is basically the absorption intensity of a microcavity with the semiconductor inside. Sorry, so this is this axis here is the piezo voltage that moves around the resonance line, the resonance energy of the cavity mode. And as you move it across certain energies, there is some avoided crossing here and then here again. And these are exactly the lines of the attractive and the repulsive polaron. So there's really a dressing of exciton polaritons inside this cavity. The exciton polaritons really form polarons. So it's an exciton polaron polariton, if you want. Now, how would this drag work? Well, imagine you have a steady current inside the semiconductor, as in this picture here. And so this steady current, as I said before, the forces on electrons translate to forces on excitons, and so a current of electrons will translate into a vector potential of a static vector potential of excitons. So this will lead to some shift of the excitonic dispersion, which is this black line here. And then I've also added a cavity photon line here that hybridizes with it, basically. So there's some avoided crossing here. And then the cavity photons live here, but they all have an average finite velocity because they are in this, you're basically hybridizing photons with the finite velocity states of excitons. Because of this polaronic dressing, and this amount here is proportional to the mass renormalization. And so at resonance, again, you get the same kind of drag conductivity. There's this 1 minus m over m star factor. There is the number of polarons and the mobility of electrons. There's factor 1/2 because essentially the polaritons are only half excitons and half photons, and you're only pulling on the excitonic part. It's suppression by factor 1/2. And then there's also some factor that accounts for excitonic scattering or exciton polariton scattering in the semiconductor. But this timescale here is expected to be rather long because these cavity photons and also the polaritons have a very light mass. So there's very low density of states for scattering. And so this tau star here for polaritons is expected to be much larger than tau for just excitons because of this effect.
I'm sorry, Falco, you have less than a couple of minutes left.
Okay, yes, fine. That's fine. So this is there's actually been already an experiment, you know, doing exactly what I was talking about. So this is a semiconductor inside a microcavity. This is kind of this rather long channel here, and then they pump the laser at some particular spot and have a current flowing in this direction. And in the absence, in the absence of this current, in the absence of this of a current, in the absence of a bias voltage, they can map out the distribution, energy and momentum distribution of the exciton polaritons by looking just at the light that comes out of the top mirror of the cavity, and there's some particular spot at some particular momentum. And if they apply a voltage, and so they apply a current through the semiconductor, they can see that this really shifts. So this is definitely some manifestation of moving around exciton polaritons in this cavity with electric currents. Now, of course, to show that this is really this Polaron drag that's there, it needs to be, you know, studied more systematically. But this is, of course, already very encouraging to know that this is working. And I think I'm right on time. This is just my summary. Is basically the main equation that you know, that you can have a direct force on neutral excitons with electric fields just by this Polaronic dressing. Thanks for your attention.
Okay, thanks a lot. Okay, so we have time for a couple of questions. If there is any, you can type on the chat, or you can directly switch on your microphone. I start with one curiosity. So, in the real systems, do you have any idea of the real lifetime of this kind of dressed excitations?
Yes. So I think typically, so the excitons typically have a lifetime of picoseconds. So okay. It would have to be rather fast. In cavities, you can extend this, you know, say to up to 100 picoseconds, which could already be enough if you plug in numbers. This could be enough to actually see some sort of movement of say the center of mass of some distribution, yeah. or to look at this you know, the momentum distribution as they did in that experiment. So that would already be enough, or basically saying that they saw some movement in the experiment is already a proof of that this is feasible in principle. The other idea would be to try to go to bilayer systems. So bilayer semiconductors where you have one material and another material that have basically electrons in one layer and holes in another layer, and then you can boost the lifetimes up to several hundred nanoseconds. Okay. Would certainly be enough to do transport, because just the recombination is suppressed by the spatial separation. Then it becomes harder to couple them to photons coherently, so that's maybe an issue. But just to show that this effect is there, I think you don't need the polaritonic dressing. You can just look at excitons and the recombination of excitons.
Okay, thanks a lot. We have a question from Matthew Output. You can switch on your microphone.
Yes, I was wondering that if you would have an impurity that's also charged in a charged bath of bosons, for example, would you then see this drag conductivity on top of the bare conductivity? So would you have like the Drude conductivity, for example, plus this drag conductivity?
Yes, yes, you would. But yes, I think you would. But this is kind of a more delicate thing, right? This you know, in principle, because of the finite lifetime of these particles, or because of scattering of these impurities, you would have to do this in an AC setup, right? I mean, remember, I've just briefly shown this, but this is something that actually requires AC frequency if this lifetime here is finite. Whenever you have a charged impurity that has a conductivity itself, it becomes much harder to distinguish this effect from the bare, say, Drude part of the conductivity, I would say. But there is some, yes. Like, for example, I didn't mention this, but this is, if you look at cyclotron motion of electrons I just mentioned briefly that if you apply a magnetic field, electrons will have cyclotron motion. So they have some frequency omega c, and the Polaron equation of motion is basically the driving force is really the oscillations of the electrons. And so in a magnetic field, you could, for example, in this case, you can see that excitons will have the same cyclotron frequency as electrons, omega c, whereas if you consider tryons, which are the charged particles, basically if you're asking the question, how can I distinguish excitons from tryons, where tryons are charged and they're dragged along anyway because they're charged, they would have their own cyclotron frequency with their own charge and effective mass, whereas excitons, they don't have a charge, and so they would only inherit cyclotron frequency, omega c, the same one, right, of the electrons. And so this would be one way of seeing this in kind of a more more complicated setup.
All right, I see. Thank you.
Okay, we thank you again for the nice presentation and the interesting topic. And we move to the next speaker, who is Sergei Klimin.
Hello.
Hello. So you can share your.
Yeah. Okay. Hello, everybody.
Okay.
I would like to tell about our recent studies in the University of Antwerp in collaboration with Hadrian Kurbidjian and Jacques Tampere. Sorry, something. Okay. In this talk, I focus first of all on different kinds of collective excitations in ultra-cold atomic Fermi gases. Unlike superconductors, different regimes of coupling strengths can be realized in ultra-cold atomic gases, varying the effective scattering length from the regime of the Cooper pairing, the so-called BCS regime, and up to the regime of pairing in real space of molecules of atoms. The collective excitations are valuable because they give us a possibility of very sensitive experimental tests of the microscopic physics of many body systems. And in condensed cold gases, they can be experimentally observed through a response function, through density response function, and even through the response function of the pair field. At zero temperature, they are already studied very thoroughly, but the finite temperature behavior of collective excitations contains still many unexplored areas. Our recent studies are intended to partly fill some gaps in this area. We use the unified approach for all types of collective excitations in ultra-cold Fermi gases. This approach is based on the path integrals over Grassmann variables corresponding to the condensation operators, and the information on the system is contained in the partition function, which is the path integral with the effective action, with the S-wave pairing using the model contact interaction, which is renormalized in terms of the scattering length. The next steps are standard and very known. We introduce the bosonic pairing field, perform the Hubbard-Stratonovich shift of fermionic variables, and then integrate out fermion fields and arrive to the effective bosonic action with the inverse Nambu tensor. The collective oscillations modes appear as a result of the expansion of this effective action in powers of fluctuations about some uniform background, not necessarily saddle point or mean field background, but even more complicated, accounting, for example, for fluctuations. But the only feature is that it is uniform. And the effective action for small amplitude collective excitations formally coincides with the Gaussian pair fluctuation action with the matrix which describes the inverse fluctuation propagator, and the spectrum of collective excitations can be determined using the dispersion equation for roots of this inverse fluctuation determinant of this fluctuation propagator. Some difficulties appeared at finite temperature when we consider the, for example, the sound modes, the long wavelength sound modes at temperatures different from 0 or critical temperature. But we can obtain the rigorous expansion when we use the assumptions that both frequency and momentum are small together with the finite coefficient which describes the complex sound velocity. In this case, we obtain the dispersion equation for this complex sound velocity. This spectrum can be found formally in two ways: numerically, using the pair field spectral weight function or the same response function, as through the maximum and the width of peaks of this response function, and analytically when we find roots of the dispersion equation. But the problem is that formally this equation contains no roots because they are hidden behind the branch cut at the real axis. In order to make them visible, we perform the analytic continuation of the dispersion equation through this branch cut and make those roots visible. It was proposed for Green's function by Nozier in 63, but now we apply it to spectra of oscillation for ultra-cold gases. Surprisingly, we find for sound velocities two complex solutions instead of one. This gives a temptation to interpret those solutions as two sound velocities known for the two-fluid hydrodynamics. But it is not completely true because the Gaussian pair fluctuation approximation works assumes a collisionless regime rather than the hydrodynamic regime. But some similarity to sound velocities still remains. What is the main? You see that those two roots differently behave as a function of temperature, and they contain the real parts and the imaginary parts we describe damping. Here I show one more value of this analytic method. Here it allows us to obtain solutions even in the case when damping is not small and even beyond the range of applicability of the quasi-particle physical picture. But the solutions in this range are still available to construct the analytic two-pole approximation for the spectral weight function or for the response function through this complex roots and through the residues for this complex roots. And this effective response function gives us the effective sound velocity and the effective damping, which remarkably coincide with those. And the shape of the whole, the total, this analytic fit for the response function remarkably coincides with the total response function. If you compare the solid and dashed lines curves in this graphs. Solid lines describe the total true response function, and the dashed lines describe this analytic fit. We see here that two roots, two poles of the propagator can be visible in the response function. And moreover, they can be visible not only in the phase response or pair field response, but also in the density response, and even very close to critical temperature, as we can see clearly in those three graphs. That this sharp peak, very close to in the low energy range, when we're close to TC, the critical temperature, is still visible. So the pair field fluctuations do not vanish and can be observable even in the close vicinity of the critical temperature. And those two-pole solution is valuable for us because it reveals the internal analytic structure of the response. We see experimentally one peak, maybe one peak, but in fact, this peak is formed by two poles. Here I can show the comparison of our obtained sound velocities with experimental data, and they are compared with this experiment is compared with our calculations using different sets of the background values of the uniform gap and uniform chemical potential from the experiment, from the Gaussian pair fluctuation theory, as was derived by Sademello and collaborators, and modified Gaussian pair fluctuation approximation, which accounts for the variation of the gap simultaneously with the chemical potential. This is the Julio and Drummond theory. And we see remarkable agreement within with our theory and experiment, of our theory and experiment. The other direction of our recent studies concerns the pair breaking collective excitations. Because this collective mode inside the pair breaking continuum still contains some open questions. Here we apply the same approach as for sound velocities, the same approach to this collective mode inside the continuum. It appears that it is impossible to obtain the spectrum of this mode, at least quantitatively correct, using some Higgs mode picture, which is based on the low momentum and low energy expansion of the pair field propagator, because those modes are strongly pinned to the non-analytic point in the complex frequency area. So as a defect in the complex area. So any expansion around zero completely forgets this non-analytic point. Those are very frequently used the Mexican head picture for Higgs modes and Goldstone modes is not relevant for these modes. They only formally can be still called Higgs, but they are physically very strongly pinned to the non-analytic point in complex frequency area.
As a result, yeah, 2 minutes left.
Okay, we obtain the dispersion relation for this mode, which is different from the very recognized results by Littlewood and Varma. Finally, we considered in this the same approach the Leggett collective modes, they were observed experimentally for superconductors such as magnesium diboride, but not yet for ultra-cold gases. But for ultra-cold gases, the two-band superfluidity is already realized. And we have shown that the Leggett modes can be observable even in the pair-breaking continuum in the strong coupling regime. They acquire only rather relatively small damping. So it will be promising to observe them in those ultra-cold atomic two-band system. And in the regime far from BEC, we obtain a new mode in the pair breaking continuum, which physically is a continuation, a deepening of the Higgs modes to the continuum. Finally, we can show all modes in the, as peaks of the phase and amplitude response functions, and we see that Leggett mode indeed goes to the continuum, as distinct from the common opinion that it cannot be observable here. And the pair breaking mode in the amplitude response is also dependent from the pair breaking continuum H. So now I come to the conclusions. So we have applied the unified approach to based on the Gaussian perfluctuation dispersion equation for all non-collective modes in a Fermi superfluid. And the obtained solutions are visible in the response function, and they are obtained non-perturbatively with respect to both damping and frequency. And the spectra are in agreement with the experiment. So, thank you for your attention.
Okay, thanks a lot. Okay, now we have time for one or two questions, so you can type the question on the chat or switch on your microphone directly.
Yeah, now I...
Okay, yeah.
I don't see other questions in the chat, or?
No, but no, there is anybody interested in making a question can switch on the microphone.
Yeah.
I start with one question, one curiosity more related to the possibility of experimentally observing the Leggett modes or what the people usually call the Higgs modes in superconductors. So, in your opinion, even if there is an overlap between these modes and the continuous states, you should be able to see a sort of resonance that is basically overdamped.
Yes,
okay. Still experimentally, you should be able to see a signature.
Yes, this is some prediction for the strong coupling regime that I can show again. This graph, you can see that Leggett modes in the cold atomic gas with two bands acquire only a low damping and have still significant peaks, can still significant peaks in the pair breaking continuum. So we can expect the observation of them in the cold atomic gases, which were experimentally realized now for superfluidity, but Leggett modes were not yet measured. We hope so.
Okay. Okay, thanks a lot. Okay, is there any other question? Okay, so if now we can thank the speaker again, clapping hands with in the reactions. Okay.
Thank you.
Thanks a lot. Okay,
I stop sharing. So.
Yeah, you can stop sharing.
Okay.
We move to the last speaker of this session, who is Rafael Flores Calderon.
Hi, hello.
Hi, hello.
I will start sharing.
Okay, yeah, you can start sharing.
Okay.
Okay, great. Okay, I'll give you an alert when you have 2 minutes left.
Thank you.
Okay.
So I'm going to present a quantized linear transport in bilayer metals. This is a work I have done with Alberto Martin Ruiz. So the presentation is divided as follows. So first, the introduction. I present little known facts about the bilayer metals and some transport properties and general properties. Then the model we consider in this work. In section 3, I present the nonlinear response in kinetic theory, which is the way we solve the model. In section 4, I present the results, which is the anomalous electrochemical transport. And in section 5, I present conclusions. So first, in recent times, topological matter and quantum materials have become of further importance in the search for new technologies, especially with the dawn of quantum computation. It is in this context that the bilayer metal was predicted and discovered. Because of their topologically protected properties, they have become potential candidates for quantum computers. Thus, studying their properties is essential. The bilayer metal is a realization of the high energy Weyl particles in condensed matter systems. The difference between a bilayer metal and a topological insulator, for example, is shown in figure 1, where on the left we have the topological insulator structure, where the band is present, the band gap. And on the right we have the bilayer metal with two very curvature charges, which are present in the Weyl nodes, which are the crossings in the band dispersion. These crossings have the effect of on the boundary of Fermi arcs, which are shown in figure 2. These were discovered experimentally and by RPS measurements. And so, as I mentioned earlier, studying the properties of this bilayer metal material and in general these topological materials are essential to their understanding. So as a topological material, a quantized quantity is expected to appear. But this has been really difficult to observe since all of the effects that might lead to quantization depend on the material properties. So they are not truly quantized quantities. One quantized quantity that was predicted is the circular photogalvanic effect. Here in figure 3 is the setup of the two-band model, and in figure B, the quantization is shown as calculated by Joel Muir and collaborators. And we see that this quantization is only for a region of frequencies, and they show that it only depended on the fundamental constants and on the relaxation time of the system. So it is different from, for example, chiral effects, which depend on material properties. So this effect was really important, and recently it was discovered that interactions tend to destroy the quantization, but it still was really essential to see that it was possible to see a truly quantized quantity, at least in this simple model. So following the lead of chiral effects in relativistic matter, we consider a gradient of chemical potential and an electric field, as shown in figure 4. We have the bilayer metal, but in this model we consider not only the normal nodes, but also the band bending and the tilt. So these nodes, which are the vinculated to the very curvature monopoles, present the Fermi surface arcs. And well, we will, I will show that if you take the chemical potential of the left node and the right node different, then a quantized quantity, truly quantized quantity appears. So the model is shown in equation 1, where we have a Hamiltonian, a low energy continuum Hamiltonian, which depends on the tilt velocity and on the momentum, and which presents, apart from the tilt, the band bending effect in the B parameter. So the eigenenergies are shown in figure in equation 2, sorry, and the band dispersion is in here pictorially in figure 5. So in figure 5a, both effects are present, the tilt and the band bending, where the blue plane is the zero energy. Then in figure 5b is present the only band bending, no tilt, and in figure C is the usual BiSML two nodes separately from each other with no band bending or tilt. So in this work, we consider only tilt in the KC direction, because this tilt actually presents with the electron hole pockets, while in-plane tilting does not produce interesting effects, and it is so extreme that the system is in a type 2 symmetric phase. Now, to solve the model, we investigate this nonlinear electrochemical current in a quasi-classical Boltzmann formalism. So in the Boltzmann formalism, we need the equations of motion for the wave packet. So in the context of this BiSML, since it is a topological material, it presents the very curvature term that modifies the acceleration of the velocity, sorry, of the charges, and thus it gives the anomalous velocity term shown in equation 3. The very curvature in our model is shown in equation 4, which can be seen that it does not depend on the tilt, only depends on the band bending parameter B. And then we plug these equations of motion into the Boltzmann equation in the relaxation time approximation, which is shown in equation 5. Now the distribution function that we use, the zero order distribution function, is the Fermi-Dirac distribution, since these are electrons. Now the current that we obtain, the non-equilibrium quasi-particle current density, is shown in equation 6, and here it's not only the velocity term that contributes, but also a magnetization current. This magnetization current depends on m, which is the orbital magnetic moment, and is a property of the wave functions and the band. So this generically describes the rotation of a wave packet around the center of mass. Now, as usual, one can solve this Boltzmann equation recursively by expressing the distribution function in orders of the fields. So in equation 7 and equation 8, we present the first order and second order distribution functions, where the second order distribution function only has the topological terms, which are present through the very curvature. Now, taking the second order current density, we find that it has the form of equation 9, and it can be put after some careful algebraic manipulation into equations 10, 11, and 12. And these currents depend on 4 functions: I perpendicular, IC, F perpendicular, and FC, which are functions of the chemical potential. And as shown in equation 13, they are products of the very curvature term times the velocity and derivatives of the zero order distribution function. So here I present in figure 6 the regions of integration, because these integrals can be done analytically. And these regions of integration are determined by the crossing points of the chemical potential through the band. So first, if the chemical potential crosses only the conduction band, then we have 2 crossing points until the Van Hoff point, which is the maximum shown here. So if the chemical potential passes the Van Hoff point, then it has 4 crossings still in the conduction band, but then it can change by moving downwards towards zero energy and have a contribution from the valence band, and thus the crossings change. So these functions have an extremum that is close to the Van Hoff point, and the difference between the I's and the F's are essentially just a sharper peak, which presents more closely towards the Van Hoff point. Here we present the results for dimensionless chemical potential and a dimensionless tilt. So the situation that is actually more interesting is shown here in figure 11, which is what if we not only have a fixed chemical potential that crosses both bands in the same level, but what if we have a left chemical potential and a right chemical potential, which corresponds to the left node and the right node. Then if these chemical potentials are different, we not only have a situation that can be solved exactly in the same way as before, but with different chemical potentials, but the conductivity tensor, which comes from the current, is a quantized quantity, which is shown in figure 10, in contrast to figure 9, which shows the conductivity for a fixed chemical potential. So in figure 10, the left chemical potential is plotted. The conductivity is plotted as a function of the left chemical potential for a fixed right chemical potential. So as it can be seen in the blue, green, and red lines, if we increase the tilt, this conductivity, quantized conductivity plateau starts to deviate slowly from the quantized value, which is 2/3. But for small tilts, this conductivity plateau is really close to the 2/3 value and horizontal. And even more importantly, this conductivity value does not depend on material properties. This only depends on the conductance quantum, which in a similar situation to the CPG effect depends on the fundamental constants and the relaxation time, which comes from the relaxation time approximation in the Boltzmann formalism.
So you have 2 minutes left.
Okay, yeah, thank you. Thus, this conductivity plateau is essentially an interesting phenomena that couldn't be predicted, since the chemical potential, since for a fixed chemical potential we had a conductivity such as figure 9, and these values of the conductivity for a left and right chemical potential are in essence 2/3, and as shown here in figure 8, 2 or -2. They only change signs, but they do not depend on the tilt or the right chemical potential. So in conclusion, we studied the nonlinear transport in a valse MML in the presence of electric field and gradient of chemical potential. And although we found extremum for a chemical potential, for a fixed chemical potential, an interesting effect occurred if we took different chemical potentials for the left node and the right node, and the conductivity was found to be quantized in a form that is shown in equation 17. And finally, using this result for small tails, since this is the condition for the quantization, we show that that there can be an axionic action derived from this conductivity and this current that is shown in equation 18 for electric fields that are parallel to the tilt. So we see that the axionic field is replaced by the chemical potential, and thus a link between a possible link between statistical macroscopic properties that are given by the chemical potential can be shown between this and the quantum topological properties of the material. Okay, so thank you.
Okay, thanks a lot. Let me open the chat. So if there is any question, you can write the question on the chat, or you can raise your hand or switch on your microphone and directly jump in. I start with one question. Experiment. So I mean, the most important parameter basically is the distance between the node and the chemical potential. So experimentally, how can you control and can you tune this distance? So you combine the application of the electric field with the chemistry of your material.
Yes, so this distance from the chemical potential and these different chemical potentials for the left and right node can be accomplished maybe through doping of the material, or it was also shown that it could be strain induced in a non-equilibrium situation.
Okay, so you can combine different
mechanisms,
parameters to control the occupations of the chemical potential. Okay.
Yeah, exactly.
Okay, thanks. Very interesting. Okay, is there any other question? Okay, so if now we can thank you again for the nice talk.
Thank you.
We clap the hands.
We'll stop.
Okay, thanks a lot. You can stop sharing. Okay, so we can close this first session of the morning. We thank you all again. And now, I mean, there isn't any break, so I leave the stage to Jeanine, who is going to chair the next session with the next two talks.
Thanks a lot. Yeah, thank you, Claudio. So good morning, everyone. This starts now the second session, which is dedicated to the study of metal insulator transitions. More specifically today, to the contrary of yesterday, the session will focus on correlated oxides. And our first talk is from an invited speaker, Javier Del Valle from University of Geneva, who will tell us about neuromorphic computing. So I will just tell you when there are 5 minutes left. So 30 minutes plus 10 minutes question. Oh, wait a second. We can't hear you. I have to unmute you.
Okay, now?
Oh, it's done. Yes, good.
Okay, so you will tell me at 25 minutes, right?
Yes, please go ahead.
Okay, so I'm going to share the screen. Can you see my slide properly?
Yes. And this is full screen?
Yeah, this is full screen. It's for
okay, good. Please go ahead.
Okay, so thank you for the organizers, for inviting me to give this talk today. I would like to start by acknowledging the funding sources. The Swiss National Science Foundation is funding me right now through an Ambizione Fellowship in Geneva. And most of this work was actually funded at UC San Diego by the Department of Energy through an Energy Frontier Research Center. So most of what I'm going to show is what I did during my postdoc at the University of California in San Diego in the group of Ivan Schuller. And now I'm continuing this work in the University of Geneva, basically working in the same topic, collaborating with a group of Jean-Marc Triscon. So we have multiple collaborators, especially these two first ones. I'll show you some synchrotron images, synchrotron experiments. Those were done together with Oleg Shpirko group from San Diego. We've done a lot of theory collaboration with the group of Marcelo Rosenberg in Paris. And we also have ongoing collaborations with Duigu Kusum in San Diego, some TM with Jim Meizu from Brookhaven, and also went with Gabriel Ramirez from the Universidad de los Andes. So this is the outline of my talk. I'm going to start by introducing what neuromorphic computing is and why is the hype about it now. And then I'm going to actually spend most of the talk talking about this, which is the voltage trigger insulator to metal transition, IMT. Every time you see IMT, it stands for insulator to metal transition. And I will focus on two things. One is what is the spatial distribution of this voltage trigger transition and what are the dynamics. And then I will give you an example of how you can use this phenomenology to implement something that might be useful for neuromorphic computing, which is a thermal Resistor. And I'll finish with some prospects. So why neuromorphic computing? So what you have here is a projection of the amount of data that is produced every year worldwide as a function of year. This is zettabytes, which is 10 to the 9 terabytes. We are now here, and you can see that in the coming years, the trend is going to explode. That is due to the emergence of the Internet of Things, more and more smart devices. And this comes together with the end of miniaturization and the end of Moore's law, and poses a big challenge, which is how we're going to process such a huge amount of data. So one solution for that is copy biology. We are actually really good at this kind of task. We're actually very good at looking at an image that it has a lot of things going on it and extract from it the basic features. So that's what machine learning did when they introduced deep neural networks. And what they do is they copy this neural network architecture, which is based of neurons that are grouped into layers. And these neurons, they receive data and they forward the data to the following neuron layers. And they do it through these synapses, through these synaptic connections. So this approach in machine learning has been very revolutionizing in many fields, but it has an intrinsic limitation. And that intrinsic limitation is that these are not real neurons, real synapses, they're just simulated entities. And they run in a normal computer, which has an architecture that is known as von Neumann architecture, and it looks nothing like a neural network, but it looks like this. You have a memory and a processor, and they are physically allocated in different parts of the computer, so you have to exchange information back and forth. And that is a slow process. It limits the size of the neural network, and it's very energy consuming. So what neuromorphic computing wants to do is go one step beyond this, and it's implementing these neural networks, but in a hardware way. So we're looking for devices or materials that have intrinsic properties that are similar to those of neurons and synapses. So these are the two building blocks that we have to emulate. We have to look for devices that behave like this. So in one hand, we have the neuron, which is an active element in the sense that it has to output a current, has to output energy. It does something called integrate and fire, which means that it takes the stimuli coming from other neurons, it adds them up, and when it's above some threshold, it fires an output, and it's volatile, meaning that after firing, it goes back to the initial resting state. And then on the other hand, you have the synapse. The synapse is passive. It's just a resistor that connects the two neurons. It controls the connectivity, and very importantly, is non-volatile. It has a memory of its past electrical history, and that's where the memory of the whole neural network is. So probably the main thrust towards implementing neuromorphic computing is based on an effect that is called resistive switching, in which you can change the resistance of a material by applying a voltage. And very conveniently, there's two basic types of resistive switching. There is a volatile resistive switching. You can see here an example. you apply a voltage or a current, and when you pass on threshold, the material becomes conducting. But when you remove the voltage, you go back the same way. So this firing-like behavior looks a lot like what a neuron should do. And this is observed mainly in materials that have an insulator to metal transition that can be triggered with a voltage. And then you have non-volatile resistive switching. And as you can see here, you apply a voltage, you change the resistance of your material, but when you go back, you don't go back the same way. So you keep a memory, which is what a CNAS should be doing. And this is a completely different phenomenon. It's way more studied, and it's, in most cases, apart from phase change materials, is based on ion drift. You just apply a strong electric field, and mainly oxygen vacancies move within the oxide. So although we've done some work on this talk, I'm just going to focus on this part. In particular, the voltage trigger insulator to metal transition, how can we use it to mimic a neuron? So this moves me to the next part of my talk, which is what are the physics of this voltage trigger insulator to metal transition? And this is a fundamental question that we need to address, because for many of you that are working in this field, you know that this is very far away from being applicable, because we don't understand many things about this voltage trigger transition. We don't understand why does it happen. We don't understand the time scales, the length scales. So we first need to understand this before making any device that can have any real use. So these are the two materials that we work with, VO2 and V2O3. They are probably the archetypical materials that have an insulator to metal transition. And they are referred to sometimes as MOT materials. This is called the MOT transition, but not always. There are some materials in which it's not a MOT transition, it's a Pyros transition, but I won't talk about that. And you can see here the insulator to metal transition. This is resistance in logarithmic scale versus temperature, and you can see there is a drop of several orders of magnitude while you cross the transition. It's very sharp drop. And down here, these are two theta scans. This is X-ray diffraction at different temperatures. And what you can see better in the V2O3 case is that as we increase the temperature, when we pass this electronic transition, there is a shift in the Bragg peak that indicates that we also have a structural transition taking place. And there has been a lot of debate whether these two transitions, the electronic and the structural, whether they're coupled or they're decoupled. One may happen before the other. I won't go into details, but you can find a lot of details here. Turns out that if you actually measure properly your structural phase fraction and your electronic phase fraction, they happen at the same time. They're completely concomitant. So now you take one of these materials, let's say VO2, and you pattern two electrodes very close together so you can apply a large electric field. And when you apply a voltage, you can induce this transition. This is what it's referred to as the voltage trigger insulator to metal transition. As you can see here, is volatile. When you remove the voltage, you go back to the insulating state. So the easiest explanation why this happens is that maybe you are just sitting here in insulated state, you are applying a current, you are causing Joule heating, and you just go into the metallic state because you are warming up. But that is not the case for some materials. And actually, apart from Joule heating, there is a clear effect of the electric field. We show here that actually, if you apply an electric field to this material, you can promote carriers to the conduction band, and those carriers will destabilize the MOT insulating state and will drive a transition into the metallic state. So how does this look like? I'm going to show you a video, which is just a collection of optical images taken with an optical microscope. And what you see here, these are two titanium gold electrodes. And I'm going to apply a current through these electrodes. And this is a V2O3 film. So actually I have to change the type of pointer. So, and here you have the voltage current characteristics. So you see that when we pass the threshold voltage, you have this filament that percolates between both electrodes. It grows thicker as you increase the current, and then when you decrease the current, it becomes smaller and eventually disappears when you go below the threshold again. Here you can see it again. So what you're seeing here, this darker area, this is metallic V2O3, and outside of here you have insulating V2O3. And the reason we are able to take this image is because there is a strong reflectivity contrast between the insulating and the metallic phases. So this is a nice video, but the resolution of this is not very good. It's just an optical image, so it's around maybe 500 nanometers to 1 micron. And that doesn't show any light on how does this happen at the nanoscale. And this is an important question to know, because one of the main challenges that we have in this type of devices is that you fabricate two devices and they have extreme variability. Two devices that they might look completely the same. When you characterize the transport properties, maybe one of them will have 1 volt of threshold voltage and the other one will have 10 volts of threshold voltage. So if we don't look deep enough what's going on at the nanoscale, we won't understand this type of why does this happen. So to solve this question, we took a sample very similar to the one I showed you in the video. This is a schematic representation. It's a BO2 film, on top of which we patterned 2 nickel electrodes. And we took it to argon, to the X-ray nanoprobe that they have in the synchrotron there. And they can focus the X-ray beam down to a 30 nanometer spot. And you can read the 2D diffraction coming from your film. And this is what you have here. You can clearly identify 2 peaks. So one peak would correspond to the low temperature monoclinic insulator, and the other peak would correspond to the high temperature rutile metal. So this allows you, by comparing the relative weight of these 2 peaks, it allows you to see what is the metallic phase fraction that you have with a 30 nanometer resolution. And if you now raster this across the film, you can get a 2D map of that metallic phase fraction, and you can do that while you're applying a voltage through these 2 electrodes. So this is what I show you here. This is a 2D map. This is the outline of the nickel electrodes. And blue means completely insulating, and yellow means completely metallic. So what you can see is that as we pass this threshold voltage, we already induce some metallic spots in the sample. And these metallic spots, the amount of metallic spots, grow as we increase this current through the device. But if you look at it, it looks very different from the video that I just showed you, in which you had this nice filament that percolates just between 2 electrodes. What you have here, what it says is that if you look close enough, if you zoom in, you have that the percolation takes place through these hotspots that are not clean, but they jump. And actually, these hotspots, they correspond to the particular position of different grains within the film. So what this shows is that we look close enough, we can see that the switching process is extremely dependent on the particular local topography that you have in your film. So what this means is that you might fabricate 2 devices and you may think they're completely similar, but just because the grain configuration might be a little bit different between both of them, that will completely change what are your transport properties. So now I move on to the next part, in which I talk about the dynamics of this transition. And this is a very important question to answer, because most of the studies, they actually focus on DC properties when you apply a voltage. But for applications such as neuronal spiking, you want to be sending time-dependent signals. So what this means is that you really need to characterize with nanosecond timescale what is the response of your device when you apply a voltage to it, or when you remove a voltage from it, because you want to do this at a high speed. Hopefully, you want to be doing this neuronal spiking in the megahertz or gigahertz regime. So what we did is we took a high-speed probe station, and we use a voltage generator to send voltage pulses into our device. And then we use a low impedance oscilloscope to take a readout of what is the current going through the device. And that gives us the dynamic response of the material. So this is what I'm showing you here. This is current as a function of time. When we send a 200 nanosecond pulse to one of our devices, and you can see that there is very little current passing, and when the pulse starts at t equals 0, actually current barely goes up because it's still insulating. But if you increase the amplitude of this pulse here, eventually you reach a threshold voltage, after which you are able to induce the transition into the metallic state. So you see here, we apply the voltage, and after some incubation time, the material becomes metallic. You induce a transition into the metallic state. And this incubation time becomes smaller as you increase the voltage that you are applying. So this tells you that it takes a few nanoseconds to induce the transition from insulator to metal. And you may wonder, what is the opposite transition? That is equally important. Know how fast does your device go back to the insulating state when you remove the voltage. So you can just measure it. This is the resistance as a function of time. So it has the metallic state resistance, and then the pulse ends, and it takes a few tenths of nanoseconds, but after that, the device cools down, and you recover the high resistance. The device becomes insulated again. But in any case, what you can see is that both the insulator to metal and the metal to insulator transition happen very fast, in the range of a few nanoseconds to tens of nanoseconds, always below 100 nanoseconds. So what this means is that if you're sending pulses, multiple pulses to your device, as long as you keep them farther apart than this characteristic timescale, they should be non-interacting. So we did the following experiment. We sent 2 voltage pulses. This is voltage as a function of time, and this is the current through the device as a function of time. So we send a first voltage that is above the threshold, so that it induces the transition, like you can see here. And then we wait some delay time tau, and we send a second voltage pulse, which is way below the threshold. So it should not trigger a transition in any circumstances. But what we see is that it triggers a transition. And in this particular example, there is 100 microseconds between these 2 pulses. That is around 3 to 4 orders of magnitude larger than the characteristic timescales that it took the system to become metallic or to relax from the metallic back to the insulating state. So what this means is that there is some sort of memory in the device that it remembers that it has been fired, remembers that it has gone to the metallic state, and now it makes it much easier for quite some time after that to retrigger the transition. It allows us to trigger the transition with less voltage. So to understand this better, we did a systematic study of this effect. So one of the things that we did is change the delay between these 2 pulses. So this is what you're seeing here. This is the probability that the second pulse will trigger a transition as a function of the separation between pulses. And you're using the second pulse here has 60% of the threshold voltage. So as you can see, the probability that this second pulse will trigger the transition goes down as we separate the pulses, but this is log scale, so it goes down very slowly. And actually 10 milliseconds after you send the first pulse, you have like 5% chance of firing again the transition. And 10 milliseconds is 6 or 7 orders of magnitude larger than the characteristic timescales that we saw a few slides ago. So this means that this memory spans several decades in time, and that it cannot be by any way explained through any cooling down effect, or especially not by any RC charge and discharge constant, which is in the nanosecond range for our setup or below that. So what can be the origin of this effect? So one thing that we thought is that maybe we have persistent metallic domains. Maybe most of the device relaxes within a few nanoseconds or tens of nanoseconds, but for some reason we have some domains which live much longer, milliseconds, tens of milliseconds, hundreds of milliseconds, and those domains, they might help us trigger transition again. So we did some resistor network simulation with Marcelo Rosenberg's group in Paris. And what they observe is the following. So here you have a distribution of the electric field when you reapply a voltage after the material has been relaxing for a while. And what he sees is that even if you have a very small amount of metallic domains, below 1%, that are residual, those they might play a very big role in shaping the intensity of the electric field, because they act focusing, the metallic domains act as lining rods focusing the electric field, and they might locally rise the electric field above the threshold limit and help trigger the transition. So, but this is just a simulation. We need to see whether we have or not these metallic domains. So in order to do that, we needed a proxy that is a good indication of the amount of metallic domains. So what you have here, this is reflectivity as a function of temperature for VO2, and you can see that it offers an excellent contrast between the insulating and the metallic state. So it is a really good proxy that gives you, it's proportional to the amount of a metallic domain, the change of reflectivity. So what we did is we modified the setup, and we focus a laser source into this gap in between the 2 electrodes. And we real-time measure what is the reflectivity coming from this material. And we send current pulses to the device and see how the material goes back from metal into the insulated state. How does it relax? And so this is what you see here. This is the metallic phase fraction as a function of time after we remove the voltage. We have removed the voltage at t equals 0. And note that this is a log scale. So what we are seeing here, these straight lines, they indicate a power law relaxation. So power law relaxation has no characteristic time scale, so it spans for several decades in time. So what we're seeing is that we have a relaxation of metallic domains that doesn't happen in a single time scale, as you would expect for exponential relaxation, but it rather relaxes over multiple time scales following power. So this type of power law relaxation is not uncommon in systems that have collective relaxation dynamics. And actually in this type of films in which you have a structural transition and you have a strain in the coexistence region between the insulated and the metallic state, relaxation dynamics, you would expect them to be collective. And one way to think about it is that you can very simply think that the rate of relaxation of a domain is going to be given by the energy barrier that it has to jump to go back into the insulating state. And if you have domains, metallic domains of different sizes, as you might expect for a system that is coupled by strain, then this barrier will depend on the size of your metallic domains. And it's been shown, this is an SNOM image of VO2 at the coexistence region. You can see insulating and metallic domains. And it's been shown that actually in the coexistence regions, there is no clear length scale in the domain size. There is this fractal pattern that forms at the coexistence. So this lack of scale in the structure might be translated into a lack of scale in dynamics, and explains why you have domains that relax at very different rates after, when they go back into the insulating state. So I'm going to move now on. I'm going to give you an example of how can we use this phenomenology to make something that might be useful for neuromorphic computing, which is a thermal-based Resistor. So this is a classic circuit representation of a neuron, how a neuron would be represented by a circuit. And you can see that it's composed of two main stages. You have on the left an integrating stage, which takes the input pulses that come from other neurons, and it integrates the charge in this capacitor. When it reaches some threshold voltage, it activates this firing stage. That what it does, it outputs a pulse of current. So this type of circuitry has been mimicked, especially using CMOS components. You have here a micrograph of one of those CMOS resistors, and they're actually very successful at mimicking a lot of the characteristics of neurons. But if you look at the size, these are close to 100 micrometers in lateral size. And that represents a problem of scalability, especially if you take into account that in non-volatile resistive switching in resistors, the current node for technology that has been shown is below the 10 nanometer pitch. So, and especially you see here these two wide large areas that are clearly not scalable. They are these capacitors that are being used to integrate the signals. And these capacitors are very difficult to shrink down because you need a minimum charge to integrate. So is there an alternative approach that we can take that doesn't depend on capacitors to integrate the signal coming from other neurons? So we propose an alternative approach, which is based on thermal integration. And what we propose is having a heater that takes the current pulses that are coming from other neurons, and each pulse will elevate the temperature a little bit. And you have that this heater is thermally coupled to a firing stage, thermally, but not electrically coupled to a firing stage that is very sensitive to temperature changes. In our case, we use a VO2, which has this very sharp dependence on the resistance. So the idea is that each pulse is going to elevate temperatures a little bit, and when you reach some threshold temperature, this firing stage is going to fire. So we actually fabricated a proof of concept device. You can see here an SEM image of such device. And here you have a schematic representation. So it is composed on two electrodes on the bottom. You can see them here. And there is a small gap, a small VO2 gap in between the electrodes. That's where we're going to induce the transition. And then on top of those electrodes, there is this other electrode with which would play the role of a nanoheater. And it would be this red strip that you see here. And the top and the bottom electrodes are separated by an aluminum oxide barrier that guarantees electrical insulation, but is a good thermal conductor. So it thermally couples both the heater and the VO2 underneath. So the idea is that we're going to bias this VO2 gap very close to its firing point, but not quite there, so that any pulse that comes through this heater is going to be enough to push the system past its firing point. And this is what we see here. This is the current, input current as a function of time, and the output current. So you see we send a pulse, a 30 nanosecond pulse through this heating element. Our device response is to generate a pulse, an output pulse. So you see that we have a device that is active because it generates a pulse of current, and that it's volatile. But there is a drawback of this is that if you look at the amplitude of the pulse that the device creates, is just 6 milliamps compared to the 20 milliamps of the input pulse. So you're actually losing intensity. And when we started this project, one of the goals that we were trying to achieve is that the output was bigger than the input, that we're gonna bias this so close to the firing point that any perturbance that comes through this heater is gonna be enough to generate a much higher amount of energy. And that's important because that means that you don't need to add amplifiers, because the moment you need to add
5 minutes, sorry, 5 minutes.
Okay, the moment you have to add amplifiers, then you have to put all the components, and you need to put silicon there. So, but we're working on that and trying to get a self-amplifying device. So I won't go into more detail about this, just show that we can mimic two other basic neuron functionalities, which is one of them is called leak, integrate, and fire, in which maybe one spike is not enough to induce the transition, but the device can integrate over time. And you can see that we send a bunch of input pulses. You can think about them as different pulses coming from different neurons, and none of them is enough to fire the transition, but the cumulative effect in the end makes your device spike. And we also have rate coding, which is a way in which the neurons actually codify analog signals into the neural network. So higher stimuli, they produce faster spiking. And what you see here is that we apply a DC input, and the higher this input, the faster the output spiking of our device. So you see 5.3 versus 8.9, you see that it spikes much faster. So this moves me to the last part of the talk, which are some prospects, what's coming next, what we are working on. And so one of the interesting things about these correlated oxides that have an insulator to metal transition is that they actually can show both types of resistive switching. When you're at high temperature, close to the transition, and you apply a voltage, you actually induce a transition into the metallic state, and you have volatile resistive switching. You apply voltage, you go to the metallic state, and you go back. But when you are at lower temperature and farther away from the transition, and you apply a voltage, you are too far away from the transition to induce it, but you can apply voltages that are enough to move ions, to move oxygen vacancies, so you have non-volatile resistive switching. So what this means is that the same material, depending on the temperature, and depending on where the insulator to metal transition is, can have neuronal or synaptic functionalities. And that's pretty attractive because that means that it is possible that we can, in the same field and at the same temperature, simultaneously have both synapse and neurons, and you would be able to pattern a whole neural network if you engineer things properly. So, but in order to do that, we need to be able to tune this transition. We need to be able to locally decide where this transition takes place, whether it happens at higher temperatures or at lower temperatures. So in some areas of your film, you're closer to the transition, and in some areas you're farther away from the transition. So we are actually working on that, on tuning the insulator to metal transition using different tools. One of the things that we are studying is the effect of radiation damage. Here you can see the insulator to metal transition in VO2 for different oxygen ion irradiations, 30 kilovolt oxygen ions. And you can see that as we increase the dose of the irradiation, this transition goes to lower temperatures and also becomes less, the magnitude of it becomes smaller, the resistance of the insulating state. So one of the things that we are working on is using focus ion beam to locally, with maybe 500 or nanometer or 1 micron resolution, tailor where we have, where we modify the transition, we can have locally neuron-like or synapse-like functionalities. Another effort is using piezoelectricity. It's patterning piezoelectric materials together with these oxide films. And that's based on this effect that we observe, that you can actually modify the insulator to metal transition a lot. This is a V2O3 film on top of a PMMT substrate that we grew. And by applying a strong voltage across the substrate, we're able to actually change what is the domain, the ferroelectric domain configuration, and we can transfer different strain to the film depending on that domain configuration. And that allows us to tune more than 30 Kelvin, where is the position of this insulator to metal transition. So when you actually put some of the domains in plane, you have a higher transition than if you have all the domains pointing out of plane. So with that, I reach the end of the talk. I've shown you different aspects of the voltage trigger insulator to metal transition. I've shown you actually how does it take place at the nanoscale, how local topography plays a major role in determining the transport characteristics of your device, the resistive switching characteristics. I've shown you that I've shown you dynamics, how the dynamics of this voltage trigger transition. Show you that there is a new type of memory that that the system remembers that it has been fired, and it really conditions its future response to other pulses. And this really conditions how you have to design devices that are going to work at high speed. And then I've shown you how you can use this phenomenology to fabricate something that behaves as a neuron, a thermal transfer-based resistor. And what we're working now is working with these films, trying to tailor the insulator to metal transition so we can implement both synaptic and neuronal functionalities in the same film. Thank you.
Thank you very much, Javier, for this beautiful presentation. So we already have a question. Daniel, can you, okay.
Yeah.
Okay.
I have a question about the basic physics involved in this switching phenomena and whether your experiment with pulses can clarify it. Because for many, many years after this switching was discovered in VO2, there was this debate whether this switching is mostly thermally driven, simply heating, Joule heating, or it is really some electronic component in it. Of course, it's definitely true that if you have S-shaped IV characteristic, you always have this metallic filament in homogeneous state. That's all fine. But what is the mechanism really? Is it really ordinary thermal runout? Because VO2 is very convenient because transition is slightly above room temperature. They can definitely have the Joule heating. But there was debate, maybe there is still something purely electronic, like direct influence of electric field, like electric breakdown or something like that. Can your experiment clarify something? What's actually the state of the art in this understanding?
Yes, so actually that's something that we tried. The problem with that is that it's very difficult. The time that it takes the system to go from insulator to metal, even if it's thermally driven, is extremely fast. It's below 1 nanosecond. So one of the things that we try to do in the line that you're saying is to differentiate them. For example, try to induce a transition using a pulse that is DC, that is always in the same direction, that and versus one pulse that actually varies between one direction and the other direction, so that the electric field doesn't build up in the same direction, but you have the same Joule heating. But in the end, those experiments are very difficult to do because when you are working at those at the nanosecond scale, the rise time of your system can play a role. And if you're doing this type of alternation between positive and negative voltage, you don't really know if you're actually applying the same amount of current in both directions. So actually, no, I think it's very difficult with pulse experiments to do this. But however, if you check this paper that we have here, we did a different experiment. What we did is made nanowires of maybe 50 to 80 nanometers so that the current is constrained through those nanowires. So by doing that, what we are making sure is that we are able in any moment to know how much power we are putting into the system. Because if you have a 2D system, you create filaments, the current is inhomogeneous and you don't know where your current is going through. But if you make a nanowire, you know exactly where your current is going through. So by doing that, we are able to calibrate how much power we put into a nanowire. So then we compare VO2 and V2O3, and what we see is that for VO2, you have a really good agreement that actually that is the power that you just need to heat up the device and cause a thermal runaway. But for V2O3, the power that you put is actually 3 or 4 or 5 orders of magnitude is smaller than the power that you would need to induce the transition. So actually Joule heating will always be there, but for some very resistive and some very clean materials, you would also have this direct effect of the electric field assisted doping. But no, you cannot differentiate that, I think, from pulse experiments. We try to do that, and maybe there is a clever way around it, but we couldn't figure it out. We had to do different types of experiments. And another thing that we're doing now is using with scanning tips that have nitrogen vacancies that can sense locally what is the temperature. We're trying to sense the temperature right before this voltage triggered insulated to metal transition happens, to see whether we reach the transition temperature or we are actually inducing the transition into the metallic state at a lower temperature. I don't know if that solves the question.
Yeah, thank you.
Thank you. So we have another question. Stefan, can you activate your microphone? Yes.
Hello, can you hear me?
Yes.
Yes, yes.
Okay, so I'm a very nice talk. I liked quite what you did, and I think it's very interesting. So I had a question on the cyclic stability of your switches, of the ones you demonstrated. Let's say for any given working conditions for a given temperature and however you operate it, how many cycles, how many firings could you make before it gets damaged?
So that actually depends on the amplitude, the width of your pulse. So if you have really thin pulses, let's say you're applying, you're applying like 100 or 200 nanosecond pulses, or even shorter, then actually more than 10 to the 14. We apply more than 10 to the 14 of these pulses, and the device doesn't seem to degrade. At the beginning, the first few pulses, you have some like training effect, but then it doesn't really degrade. However, if you start increasing the length, the width of these pulses, and you say, let's say you go to 1 microsecond or a few microseconds, then what happens is that you're heating too much your films. And that actually plays a role. And what we see is that after sending 10 to the 10, 1 microsecond pulses, you can still see, you can start to see degradation. You see that the resistance of the insulating state starts going down. So actually making short pulses to avoid heating too much is really important, because otherwise you are just destroying your film, because you heat it. We did some console simulations and you can reach several hundreds of degrees Celsius.
Okay, thank you. So as long as you keep it short, you can essentially work it for very long times.
Yes.
Thank you.
Okay, other questions? No, so I have one actually. So on the Resistor side, with phase change materials, and there we use ovonic threshold selectors with using ovonic threshold switching to fire and to write the memory. Have you an idea on how competitive this your proposition is in comparison with those resistive phase change plus selectors that are developed by industrial companies, big companies like IBM or something? So how do you think that these here will be competitive regarding the size, the power that you need to use it? How far are you from developing something?
So actually, I heard before this selector, it's basically to avoid sneak paths, right?
Yes.
So to be sincere, I don't know the state of the art of selectors in to avoid sneak paths, so I cannot really compare. So I cannot really give you a clear answer on that.
Is already what you show here developed into actual network to do some computing or preliminary?
No, so it's not developed into. We don't have multiple devices, and the main reason why we don't have multiple devices is because of this device-to-device variability. There is a strong variability, you know. Yeah, like you fabricate 10 devices and they will have like 2 volts, 6 volts, 7 volts, 3 volts of threshold voltage. So until we don't solve that problem, we cannot go to the next step, which is studying a lot of devices. It's not reproducible enough right now.
Okay.
There are other materials that are more reproducible, like niobium oxide, but they're also bigger devices. So it seems like the smaller you go in the device, the less reproducible it becomes, because you are more sensitive to the particular grain structure of your film.
Okay, thank you. So we have a question from Zeshko. Yes.
You can hear me. So I actually kind of want to relate to the question of Stefan, because your results that you're showing here are actually quite ideal for high-speed AC circuits, right? Because, I mean, if we, for example, nowadays in, I don't know, passive optical networks or something like that, you have signals that are reaching 50 gigahertz or 100 gigahertz. So the symbol length there is, well, definitely like, I don't know, 40 picoseconds or something like that. So my question would be here, for this particular device, would you be able already to speculate about the frequency range in which it could operate ideally, let's say?
Yes, so in the lab, we are limited by the rise time of our probe station. So, you know, You have long wires that go to your sample from the generator. So that limits you maybe to a 300 picosecond rise time. It's very, very difficult to go below that. But it's faster than that. So as fast as you can go with your setup, this transition can be faster than that. And there's people who have done optical switching, in which they send with Pampro experiments, they say the light pulse, and they demonstrate switch as short as a few tenths of femtoseconds, as fast as their device goes. So in reality, there is no physical limit that has been found yet to how fast this happened. The fastest it has been induced, it's in the tens of femtoseconds. And the only reason that we electrically cannot induce it faster is because our setup is limited to maybe 500 picosecond rise time. So in principle, yeah, you could really, really go very, very fast with it.
That would actually be quite interesting to see, yes.
Maybe the two of you can chat later. So we need to move on with the next speaker now. So thanks again, Javier. And,
thank you.
So our next speaker is Paolo Franceschini from University of Brescia, who will tell us about the optical control, yes, of the metal insulator transition.
Okay, can you hear me?
Oh, weekly, I think.
Here is it better?
Yes.
Okay.
Yes, it is.
So try to keep this here. So, good afternoon to everyone, and thanks to the organizer for giving me the possibility to present our recent work. So, in this presentation, I will introduce our application idea of the electronic coherent control. And after this, I will describe the V2O3 material like a possible application platform, considering also its insulator to metal transition. After this, I will describe our preliminary evidence for the possibility to coherently control this insulator to metal transition by light. And after this, I will discuss the conclusions and the possible perspective. So, first of all, coherent control is a method that has been widely employed in order to control in a dynamic way the reactions, chemical reactions by light. In particular, if we consider the simplest description with a two-level system, this technique allows to change the state of the material from the ground state to the excited state by exploiting the phase of the electric field impinging on the system. In particular, this method was firstly introduced in atomic systems, because on this kind of systems, the coherence is maintained on a time scale on the order of 100 femtosecond, 1 picosecond, so quite long coherence time. Recently, there have been some reports on the application of the coherent control on solid-state systems, in particular, the possibility to switch materials from the insulating to the metastable metallic state by employing a double pulse excitation scheme. In this particular case, reported in this work, in order to govern the transition, a K-structural mode was adopted, so a vibrational degree of freedom was exploited. Therefore, in solid-state systems, up to now, only the vibrational coherence have been exploited, which has a coherence time on the order of tens of femtoseconds. So experimentally is something which is achievable. However, nothing has been, up to now, nothing has been reported concerning the electronic coherence. So the possibility to exploit this feature in order to change the phase of a material. This because if we consider the time scale in which this coherence is lost, the electronic coherence is vanishes on a time scale of 10 femtoseconds. So this dephasing is mainly due to electron-phonon coupling or electron-electron interaction. Therefore, if in order to exploit the electronic coherence to change the state of a material from an initial to a final state, it is necessary that the manipulation of the population is done on this ultra-fast time scale. Now, I will characterize the kind of landscape, energy landscape we would like to address. In particular, we deal with a system which possesses two phases, a metal state and an insulating phase. These two phases are connected through a Mott transition. Therefore, in particular, we are interested in correlated materials. This because the insulating phase of Mott materials or correlated materials possess a band structure like the one reported in this panel. So there is a gap which is opened due to the correlation, and therefore if in some way the population is changed, also the band structure is strongly influenced by this interaction. For our final idea is connected to the possibility to control the shape of the potential in the free energy diagram by opportunely manipulating the population by exploiting the phase of the electric field. After this, I will now introduce our specific material, which is the Mott insulator V2O3. Particular, this vanadium oxide is characterized by strong on-site electronic Coulomb repulsion, which gives rise to a variety of phases for this. If we start from the low temperature phase, this material exhibits a multi-band structure, which is mainly due to the two valence band of the vanadium atom on the d orbitals. Then, due to the crystal field acting from the octahedral configuration of the oxygen atoms, there is this multi-band structure in which we have an occupied lower rubber band and an empty upper rubber band, and a third band which interacts with the lower one. The insulating feature can be clearly seen if we look at the optical conductivity at low temperature, in which we see that at low energy, the conductivity is 0 and then become non-zero after a certain threshold. B2O3 then undergoes an electronic phase transition from insulating to a metallic state when the temperature is raised. And usually the transition is around 150, 170 K. As you can see by looking at the optical conductivity, you see that at the high temperature, you have a non-zero conductivity also at low energies. If we now concentrate our attention on the optical properties in the visible part of the spectrum, we can see the reflectivity variation across this insulator to metal transition. In particular, here I report the hysteresis loop formed by the heating and the cooling changes of these phases. As recently reported and demonstrated, there is the possibility to photoinduce this transition from the insulating to the metallic state by an optical excitation. Here on the right panel, I reported the differential reflectivity as a function of the time delay between one single pump excitation and a probe. If we compare the variation of reflectivity we obtain in this panel and on the right panel, we see that the system really goes from the insulating to the metallic state. However, the role of the pump is extremely interesting because when the system is excited by the external pump, there is a change in the orbital occupation within the band that induces a change of the band structure itself. Therefore, there is this phase transition. At this point, it is important to underline that this phase transition is the photo-induced phase transition is strongly incoherent, because as you can see from this trace, from the differential reflectivity traces, the metallic state is reached after tens of picoseconds. If you remember, and considering the typical time scale on which the coherence is lost, when the system arrives in the metallic state, this has completely vanished. So when the material is excited by one light pulses, the result is an incoherent transition. Is it possible, however, to overcome this limit, or is it possible to go from the initial insulating state to a final state through a coherent transition? So in our scheme, we adopted a double excitation of the system. So in our case, the initial state is excited by two pump pulses, which are coherent in phase. In particular, in order to overcome the limit on the coherence time scale in solid state system, these pulses must be very short in time. So quite challenging under an experimental point of view. So now I will show you our result. In particular, first of all, on the left part, you see our sketch of our experimental setup. So our sample is excited by two pump pulse, whose delay can be finely tuned. The final state of the system is probed by a third pulse, which arrives at longer delays. After the interaction with the sample, the probe is dispersed on a spectrometer. On the right part of the slide, you see a typical measurement in which we report the differential reflectivity as a function of the detection energy, which is the probe wavelength, and a function of the excitation energy, which is an kind of energy connected with the pump-pump delays. If we, just to better understand our results, if we integrate the data along the excitation energy, we obtain a standard pump probe spectrum, which means that we have an information about what happened when the system is excited only by one pulse and then detected by a second probe. Instead, what is more interesting is the information we get from an horizontal slice. First of all, this cut is corresponds to a single probe wavelength, and the data obtained corresponds to a scan of the different pump delays. This scan gives rise to an interferogram whose Fourier transform produces this spectrum. In this graph, we are comparing the differential reflectivity spectrum at a fixed probe wavelength and the pump spectrum which excite the system. In this, and clearly you can see that there is a difference in the width of the two spectra. In particular, the pump spectrum results wider than the signal, the correlated signal.
2 minutes. You have 2 minutes.
Thank you. This difference can be recognized if we compare the interferogram from which these spectra are calculated. In particular, here I report the blue traces, which is the signal describing that the system is oscillating between the insulating to between the insulating and the metallic phase, while the red interferogram is the autocorrelation interferometric between the two pump pulses. Clearly, you see that the blue interferogram is wider than the red one. And this gives us an information about the fact that the coherence of the system is maintained for a longer time with respect to the excitation pump pulses. This leads me to the conclusion. So during this presentation, I reported the case of V2O3 as a promising system, thanks to which it is possible to control the insulator to metal transition in a coherent way. And finally, I have shown some persistence effect of the coherence in a photo-induced phase transition. Of course, this is still a work in progress work. So we are we have still some steps to be described, to be investigated. In particular, possible new investigation can be study the role of the coherence in the vicinity of the transition, and for example, try to explore different positions in the V2O3 phase diagram, or look at other solid state systems in which that may have a longer decoherence time. With this, I want to thank all the people involved in the project, so the ultra-fast optic groups in Brescia and the one in Milan, and the functional nanosystem group in KU Leuven. And finally, I thank you for your attention.
Thank you very much for this very interesting talk. So I think now we are convinced that vanadium oxide is promising. I'm sure there are many people interested in this system in your talk, so I suspect there will be questions. Anyone? Please raise your hand. Okay, maybe they're already working on something with vanadium oxide. So I ask questions. I'm not at all working in that field, but now I'm surprised by these oscillations that you observe with the coherent control between the insulator and metallic phase, as I had understood that the transition was mainly between two phases, monoclinic and coronum, right? And here, this is in a single phase where you oscillate between the two states.
So, thank you for your question. So, if we consider, in general, the thermal or the thermal transition is from the low temperature to the high temperature phases, in which also there is a structural transition between these two states. Sorry, can you hear me?
Yes.
Okay, sorry. And why? And also in this, but in this, in the coherent, in this oscillation, I'm saying that the system oscillates between these two band structures, but regarding the kind of phase in the out of equilibrium situation, this is something still under debate.
Okay, because the times are so small that your structure does not have any time to relax. I see Claudio, you want to ask a question?
No.
No? Ah, okay. My mistake.
No, I can add a comment about that. So, I mean, this time scale that is very, very small, you refer to, but then, I mean, the state of the system is probably after 100 picoseconds. So this phase delay is the delay between the two pumps. So actually, you have the time to relax to a new phase, because, I mean, then you probe the system after 100 picoseconds.
Ah, yes.
Okay, so this delay is the delay between the two coherent pumps, and then you probe your system later on. So basically what
Okay.
I'm showing is that the final state after 100 picoseconds depends on the phase delay of the two pumps that are delayed within a few femtoseconds.
Okay, I understand.
So yeah, sorry, I have a small question. It's also related to the experiment. Then yeah, because I was yeah, it's related to that, because then you fix the probe, the pump probe delay basically. But I was wondering, I guess experimentally it becomes very complicated to do now variation of the delay, right?
Do you mean the delay between the two pump pulses?
And the probe.
Okay, I can use this sketch, which is a very schematic of our probe, our optical line. So the two pump pulses are generated thanks to a collinear interferometer, which creates two replicas of the same pulses, while in this case we have a stronger control on the phase stability of the two pump pulses in order them to be coherent. The third pulse, which is the probe, actually is arrive on the sample after being delayed by a simple delay stage. Because in this case, we don't have to, we don't need to pay attention to the coherent relation between the probe and the two pump pulses. The most important aspect is the coherence between the two pump excitations. So that's why we have a simple delay line for the probe.
Okay. Okay, thank you. A last question, Matthew, can you open your mic? Yes.
I don't have a question.
Oh, sorry. I thought you raised your hand. My mistake. Okay, so there are no more questions. So I think we can thank our speakers for the session. And I remind you that there will be next session tomorrow morning at 9:30.